Good morning, guys. Welcome to another episode of. Okay, so we've been talking. Yeah, we've been talking, and I think like there are some things that are not so clear. Just can you close it down? And I think there are some things that are not so clear. We talked about three multilinear representations, right? Can we remember? What are they? Dense, sparse, and evaluation, right? So, like, each of them, like, okay. If we have a polynomial, yes, I'm started recording. So, if we have a polynomial, we can represent that polynomial in the coefficient form, right? We can also represent that polynomial in the evaluation form, right? Does that make sense?
Yeah.
So, even in the coefficient form, we can represent it in the sparse and the dense representation, right? And in the evaluation form too, we can represent it in the sparse and in the dense representation, right?
The evaluation form is by default is dense already.
Yeah, by default it's in dense,
Yeah.
but we can as well represent it in sparse,
Yeah.
right? Do we agree? Do we agree? We have a polynomial. Let's say, which polynomial should we use? The popular polynomial. 2ab plus 3bc. Right. So this polynomial, we can represent it in the coefficient form. And we can also represent it in the evaluation form. Right? In the coefficient form, we can decide, like, it depends, everybody may have like different ways of representing it. Right. In the coefficient form, since it's three variables, we can have like 2, 1, 1, 0. Does this make sense? And 3, 0, 1, 1. Right? Does this make sense? Where this is A, B, C. A, B, C. This is a sparse representation, right? The coefficient forms sparse representation. Do we agree? Because it's possible that this polynomial may still have had 0 A, B, C. Right? In the dense coefficient representation, we will need to like specify this 0 A, B, C. Right? Because we are specifying like all possible combinations of A, B, C, the alphabet, like number of variables. Does that make sense?
Yeah.
So this like the sparse coef form. for the dense, it's going to be like a whole lot of. We're still going to have like this, right? Zero zero zero, right? And like we're still going to have like this 110, this 011. Okay, so we're going to have 0. Now this makes sense. Like all possible combinations of A, B, and C, but their coefficient is going to be 0, right? So basically, so this is the dense rep, still for the coefficient form, but there's literally no need for all these ones, right? Because their coefficient is 0. But in the dense rep, we have to represent it. This last two, like there are more. I'm just stopping here so that, because in the dense rep we need to represent like 000, which is the constant, where A, B, and C. Yeah. We also need to represent like 001, which is C. You get the 010, which is B. 011, which is BC, which is now this one here. Right. Huh? It's
It was lacking.
okay. But it's okay now, right? Okay. So this makes sense up to this point,
Yes.
right? So now let's talk of the evaluation form. So the sparse and the dense for the coefficient form makes sense, right? Let's talk of the evaluation form now. Still at 2AB plus 3BC, right? We need to evaluate it over all possible combinations of zeros and ones. We need to evaluate it over the Boolean hypercube, right? So when we evaluate it, what are we going to get? That's 00003, right? Is it? Then 0205, is it? Okay, 0025. So this is the evaluation over this guy, all possible combinations of zeros and ones. This is the evaluation, right? So this is, which representation is this?
Dense for evaluation.
The dense for evaluation form, right? And if we want to represent the sparse for evaluation form, how are we going to represent it? We index it. We can decide to go that route because we could also decide to go that route for this guy, right? But let's just like outline. Let's just outline it.
So which one is the dense?
For which one? For this one. This is the dense. But I cancelled all these ones, but in the dense they will be there.
That is the dense.
Yeah,
The dense, all of them will be
everything has to be there.
dense fast. Just one.
Makes sense, right? So for this same one, like for this evaluation form, the sparse is going to be um, 3. This will be 0, 0, 0, 0, 0, 1, 0, 1, 0. That's 0, 1, 1, right? Then we have 2. This will be 1, 1, 1, 0, right? And we're going to have 5, which will be 1, 1, 1. Does it make sense? It doesn't make sense. Okay, so this is the evaluation at 0, 0, 0. This is the evaluation at 0, 0, 1. This is the evaluation at 0, 1, 0. This is the evaluation at 0, 1, 1. So that's why we have 3, 0, 1, 1. Right? You get? So this 1, 0, 0, 1, 0, 1, 1, 1, 0. 1, 1, 1. You get? This wants to look like the sparse of the coefficient form, but they are not the same thing. You see 5 is not here. Right? So this is sparse for a vowel form. Does it make sense? Sure. Okay. Where did you get confused? I know it can be confusing. Right. It can be confusing. You know, we have, how many ways can we represent a polynomial? We have like coefficient and evaluation, right? You can either represent that polynomial in the coefficient form or in the evaluation form, right? In the coefficient form, that's basically just the way it is, like this. In the evaluation form, we'll need to evaluate that polynomial over the Boolean hypercube, which is this, right? So still in the coefficient form, you can have like the sparse and the dense representation, and in the evaluation form, you can have the sparse and the dense representation, right? For the coefficient form, this is a sparse representation, just the values we are dealing with, or just the coefficients that are available, right? But you know that this polynomial has 3 variables. So there also exist other combinations of A, B, C, but they have a coefficient of 0. You get? Does that make sense? In the dense representation, we are also going to represent all those combinations with their 0 coefficient in the dense representation of the coefficient form. But why use up all this space? It's unnecessary. We know that it's 0. Right? Are we following? Are we sure? Over. Eh? Huh?
Can be ordered.
Which one?
The dense of the coefficient.
Yeah. No, it's just because I'm giving an example. That was why. Yeah, you need to start from like 0, 0 at where A, B, and C is not there, right? Yeah, in the coefficient. Okay, so now let's talk of the evaluation form. In the evaluation form, we also have the sparse and the dense representation, right? For the normal one we know that we've been working with is the dense representation in evaluation form, where we need to represent all the evaluations over the Boolean hypercube, which is this, right? We can also decide that, oh, since some of these values are zeros, there is no need to store it, right? There's no need to store those values. So we can still represent this evaluation form in the sparse form, which is now this. So we just store the evaluation and the points where when we evaluated them, we got that evaluation. Does it make sense? Same thing here, like 2, which is the evaluation. Then where did we evaluate it to get 2? At 110, right? And 5, which is the evaluation. Where did we evaluate it to get 5? At 111. So we are going to store it this way.
This one is the value of the Boolean hypercube.
Yes, this is the evaluation over the Boolean hypercube. We can still think of this as the evaluation over the Boolean hypercube, but we're storing, yes, it's sparse form. We're storing the places where we have values. You get? So the evaluation form we told people to implement is this one, the dense representation of the evaluation form, right? Why did we tell people to implement this? Huh?
To have the evaluation of the
Yeah, because it's easier to visualize basically. Like if you want to think of it graphically, it's easier to think of it with respect to this way, right? So now let's explore this dense representation for the evaluation form. A polynomial is still 2ab plus 3bc. Huh? Let's talk. Sad. Does this make sense? Or let's go this other way. Okay, so I'll think of it this way. Right? So this is the evaluation over the Boolean hypercube. Already. We already have the evaluations over the Boolean hypercube. So if I tell you to evaluate this polynomial at, if I tell you evaluate 2ab plus 3bc at 100, what is the answer? It's 0, right? Do you need to evaluate it again? You don't, right? Because it's here already. You just come here and pick the value. Does that make sense? If I tell you to evaluate it at 1, 1, 1,
5.
do you need to evaluate it? You don't, right? Because the evaluation is already here. So you just come here and pick it, 5. If I tell you to evaluate it at 2, 1, 1, do you need to evaluate it at 2, 1, 1? Yes, because 2, 1, 1 is not here, right? So anytime we tell you to evaluate it at any combination of zeros and ones, we don't expect it to evaluate, right? Because you already have that evaluation. You calling the evaluate function is basically just redundant. It's redundant, right? Does that make sense? Okay. So now let's look at something. Okay. So if we partially evaluate this at a variable, like if we partially evaluate this evaluation form now at a variable, what are we going to get? Let's say we partially evaluate it at a is equal to 2.
You get an array that is like half.
An array that is half the length, right? And that new array we are going to get, is it still the evaluation of a polynomial over the Boolean hypercube?
Yes, for two variables.
In 2 variables, right? It's still the evaluation of a polynomial over the Boolean hypercube, but in 2 variables. Do we agree?
Yes.
So let's evaluate it, right? At a equal to what? 3. Let's evaluate it at a equal to 3. Should we evaluate it at a equal to 3? No. Let's evaluate it at a equal to 0. If we evaluate this polynomial at a equal to 0, what are we going to get?
We don't know.
We don't know, right?
No, if we evaluate at 0, that means
We are going to
we are
get,
retaining B and C.
if we evaluate at 0, we are going to get 0, 0, 0, 3.
Yeah.
If we evaluate it at 0, we are going to get what?
0, 0, 0,
0003.
yeah.
Is that what we are going to get?
Wait.
If we evaluate this polynomial at 0,
Yes.
we are going to get 0003.
Yes.
How much? How much? Eh?
At 0,
Yes.
Yes. B and C, because B and C does not have any value, so B and C still have that tendency to be either 0 or 1. It's only A that we are certain is 0.
Okay, if they're calculating as 0, we should get 3.
Actually, you're right. If we evaluate it as 0, we are going to get, if we evaluate it at a variable, we are going to get a new array, a half the length, right?
Yeah.
If we evaluate it as 0, what do we mean? We say we want to evaluate at a equal to 0. We have this value already, a is equal to 0. A is equal to 0, right? A is equal to 0, a is equal to 0. Right? We're supposed to get a new array that is half the length
half the length.
of this one. So when we evaluate it as 0, we are basically saying, give us all the places where a is 0. Do we agree? I'm not sure we agree. Let's work it out. I'm not sure we are. No, we are not talking like we agree. Let's work it out. Right. So we said we are going to get all the places where a is equal to 0, which is 0, 0, 0, 3. Okay, now let's use our interpolate and evaluate function. We all know how to get the interpolate and evaluate, right? Okay, so what is the formula for interpolate and evaluate? Why what?
F of R equal to Y.
Okay, let's say f of x is equal to what?
Is it F of S? That be F of R.
Let's just,
Anyone.
or let's forget about it. Give me the formula.
Y1
Uh-huh.
plus R bracket Y2 minus Y1. So R is
What is this formula?
R is the linear interpolation.
Huh?
Linear interpolation.
Linear interpolation and evaluation.
What is the general term for this formula? The equation of a straight line.
Yes.
How is it the equation of a straight line?
Y1 is the intercept. Y1 is the intercept. Y2 minus Y1 is like the gradient.
What is the equation of a straight line?
Y equals to mx.
Y is equal to mx plus c. Where m is the slope, right? C is the intercept. Where m is the slope and c is the intercept, right? What is the slope of a line? y2 minus y1 all over x2 minus x1, right? Eh? Oh, sorry. Sorry. No, this is basically what we've done already, right? I'm just showing us another way to derive it, right? So we can decide to use the normal interpolation and evaluation, but everything will still give us, it's like different ways to get the same result. Or maybe I should not be talking about this so I don't get us confused.
You can proceed.
Okay. So in this case, our x2 is 1, right? And our x1 is 0. When we have a straight line, okay, let's just draw. Let's say this is the straight line. Our origin is 0, 0, right? This is, or let's just, with respect to the x and y, this is 0, this is 1, right? So that's just basically what we are trying to achieve here, right? We say when this x2 and x1, let's just make it easy for us to understand. X1 and x0. This is the same thing. Do we agree? We are just saying 0 is actually the starting point and 1 is the end point. When we use like x2, x1, we're just saying like 1 is the starting point, 2 is the end point, right? So if we have the evaluation of a line at x equal to 0 and x equal to 1, with these 2 points we can draw that straight line, right? So that's basically what we are just reducing this problem to. Does that make sense? So what this means is that when we evaluate at 1, what is the y value? Hmm? Which example should we use?
7.
Wait, let's just use like a random, like I'm trying to, okay, let's still use the y1 and y0, right? If we evaluate the polynomial at 1, we want to get y1, right? If we evaluate the polynomial at 0, we want to get y0. Does that make sense? Because if we think of the pair, it's usually x0, y0, right? x1, y1, right? It seems to have lost some people. So this will give us 1, right? So if this gives us 1, it basically means our m, we can think of our m when we are dealing with the evaluations at 0 and 1. We can think of our slope as y1 minus y0. Yes, which is what we have in this formula. y1, y0. This should be 0. That makes sense. Are we sure? So why mx plus c reduced to this is because we stated that we are dealing with the evaluations at 0 and 1. This thing is still mx plus c, right? But why it's reduced from mx plus c, where r here is our x, right? So why it's reduced from mx plus c to this is because we stated that we are dealing with our evaluations at 0 and 1. So when we evaluate at 0, we want to get y0. When we evaluate at 1, we want to get y1. Does that make sense? So that's basically why it's reduced from mx plus c, which is the normal equation of a straight line, to this. So let's go back to our original problem.
Sorry, let's go back to if we're already saying that x is 0 and 1, why is x still there in the... Is it not supposed to be...
This x now is like where we want to evaluate that.
So what is the output of this whole thing? Is it the constant?
The output will be the output of which one? This one.
Yes.
It's going to give us y, which is the evaluation at the point x. I hope I'm not confusing you people. Okay, let's forget about all this now. Let's go back to our problem. We have already stated, right, that if we evaluate at a equal to 0, we want to get this array, right? So now let's actually do that evaluation. and see if we get this array. I'm not copy this. Okay, so let's do the normal pairing. Right. How are we going to pair? If we want to evaluate at A. Zero 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 1 0 0. Right. Okay. So 0 0 0. We pair it with 1 0 0. Right. Uh-huh. 1 0 1. Okay. Uh-huh. 1 1 1 0 and what? 1 1 1. Right. Do we agree? Okay. So now we are going to use that interpolate and evaluate formula. So if people said this y0 plus what? R y1 minus y0. This makes sense, right? This is just the normal interpolate and evaluate. What I was trying to do here was like to explain the concept. But let's just forget about it for now, since we already know how to derive this. You get? So for 0 0 0, right, that's 0 plus what is our R? 0, right? Because we want to evaluate at A equal to 0. So we'll use 0 for our R. Does that make sense? Y1 is what? Still 0, right? Right. Let's just this 0 0, right? This is 0 0. This is 0 2, right? And this is 3 5. Do we understand what this is? So we're just doing the pairing. Right, we're just pairing the values. So this is clear. Is it?
Yeah.
Are we sure? Are we sure? If you're not clear, or please ask. So our y1 is what? This is basically y0, right? And this is y1. Do we agree? Are we sure?
Yes. Or we should just leave the Y1 and Y2.
Okay, to y1 and is it y1 and y2 like everybody's comfortable with? Y0 and y1 still works, right? I think I've lost some people. Eh? No, like
I'm following actually.
you're following. No, I didn't ask a question. I'm like, who did I lose? Eh? Are we following? Okay, so y1 is 0, right?
Yeah.
And y0 is 0.
Yeah.
When we evaluate this, what are we going to get? we're going to get 0, right? Good. And basically, in our array, you know what? This guy is out, right? Like this A guy is out. So, where we have 0, 0, our new evaluation is going to be equal to this 0, right? Right, because we are combining these two to get this new one. Is it making sense? Okay, now let's work with 0, 0, 1 and 1, 0, 1. So 0, 0, 1 and 1, 0, 1 is 0, 0. So we're basically going to still get the same thing, right? Which is 0. Does that make sense? So at 0, 1, which is this guy, this is 0, 1, this is 0, 1. So I'm basically combining it to get the new 0, 1. It's going to be equal to 0. Right? At 0, 1, 0 and 1, 1, 0. What are we going to have? What's our y 0? Plus, what's our r? Our r is 0, right? What's our y 1? 2. What's our y 0? 0. Huh? You sure?
I'm okay.
Are you sure?
Yes.
Eh?
Yes.
So if we evaluate this, we are going to still get 0. Because this 0 here will turn this guy to 0. So 0 plus 0 is equal to 0. Right? So at, what is it? This 1, 0. Right? So we're combining the two of them basically. And when we combine the two of them, we still get 0. Because they are on a straight line. So I just interpolating. The combining I mean is the interpolation. We get. So at 1, 0, we get 0. How about at 1, 1? At 1, 1, what is our y 0? 3. Plus, what is our r? 0. What is our 5 minus 3? This guy will go off, right? Because 0 times anything is 0. So we have 3 plus 0, which is 3. So at 1, 1, after combining this guy, this 3 and 5, we got 3. Does this make sense?
Yeah.
Are we sure? Are we sure?
Yes.
So this basically still gives us, if we arrange it now in an array based on the evaluations, right? So at 0, 0 is 0. At 0, 1 is 0. At 1, 0 is 0. At 1, 1 is 3. Is it the same thing with the other one?
Yes. So you can just
Right?
you can just add that guy and then the first one.
Does it make sense? Does it make any sense? It's not about making sense. Like, does it make any sense? So we just performed all this computation only to go and pick the first half of the array. We evaluated at a equal to 0. We're basically saying, give me all the values when a is equal to 0. Does it make sense? Let's now evaluate at a equal to 1. We are going to evaluate at a equal to 1 now. But does this make sense for the evaluation at a equal to 0?
Yes.
One. Since I feel we now know that since we are able to get the first four when it was 0, if we do at it, we now get the second half.
Okay, so he's trying to say that you're trying to say, oh, it's you that is trying to say. You get? He's trying to say that if we evaluate at a equal to 1, that we're going to get the second half. Is it true?
Yes.
Why?
We have seen from
Because A is 1.
Is it because of what we saw from that one that we're concluding? Is it enough for us to conclude?
by experience, we have seen that there's
By
pattern.
implication.
By implication. Okay, let's just do it by hand. Right? Let's just do it by hand and see. Please, are we following? Sure? Sure? Okay, so we still have the same old stuff. We still have the same old stuff. And we want to evaluate at a equal to 1. Right? Our pairing will still be this normal pairing. Right? Do we agree? It's still A. Right? Still the normal pairing. Right? All of us still remember how to do the pairing, right? Are we sure? We are not sounding like we remember.
Where this guy is changing.
And the other ones are constant. We remember, right?
Yes.
So we want to check when A is equal to 1. Still our same old equation of a straight line, right? What is that equation again? No, the one like everybody. Y 0 plus R Y1 minus Y0, right? Now we are saying we want to evaluate that A is equal to 1. So our R will basically be 1 in this case now. So for 0, 0, right, it's a straight line. Our Y0 will be what? For 0, 0. Our Y0 will be what? 0, right? Plus our R is what? 1. Our Y1 is what? 0. Minus 0, right? What is that? 0. And we know why it's 0, 0, right? because like this is a constant line. You can still think of it as a constant line. I don't want to confuse us because the last time I was trying to explain this, it seems like I got a lot of people lost. So, but we agree that at 0, 0, we'll get 0. We agree? How about at 0, 1? What is our y0? 0. What is r? What's our y1? No, our y1. What of our y0? Still 0, right? So, what is it going to be? Right? Okay. How about at 1, 0? What's our y0? 0, right? What's our r? y1? What is this going to be? 2 minus 0 is 2, right? Times 1, 2 plus 0. How about our y0 is what? 3. Do we agree? Our y0 is 3. Okay. What's our r? What's our y1? 5 minus 3. Right? 5 minus 3. 2. 2 plus 2 times 1. 2 plus 3.
5.
Does it make sense? If we arrange this in an array based on these values, we have 0, 0, 2, 5. Is this equal to what we predicted? 0, 0, 2, 5. What's the second half? 0, 0, 2, 5. It's correct, right? So, if we have that polynomial and we said we want to evaluate at a is equal to 1, did we need to actually do that evaluation? No need, right? Because we basically have where a is equal to 1, which is all these points here.
Did you say logic approach, let's say B?
Yeah,
If it happens that you want to evaluate at any value greater than 0,
we're going to get to that. We're going to do it. So. Should we try with B?
Yeah.
Let's try with B. Okay. Still my same old guy, right? So what to evaluate at B? B equal to what? I want to evaluate at B equal to 0. So what is going to be our pairing for B? 0, 0, 0. So 0, 1, 0. So that's basically 0, 0, 0 is 0, right? 0, 1, 0 is 0, right? Let's call this our y0 and our y1, right? Because that's where B, this is where B is 0, right? And this is where B is 1. So that's why it's like y0 and y1. What is the next one?
0, 0, 1.
0, 1, 1. Okay. Next one. Okay, that one is 0 to 3. What's the next one? That's 1, 0, 0, which is 0. 1, 1, 0. So, what's the last one? Okay, so that's 0, Abby? Pairing with 5. Who can predict when we evaluate at b equal to 0? Who can predict what we'll get?
0, 0,
I'm going to get b equals to 0. I'm going to get
0,
0, 0, 0, 0.
We're going to get 0.
0, 0, 0.
That's your prediction, right?
Yes.
Okay.
B 0. And R 0.
I not say anything.
Why not?
It's people that are saying it too. It's people that are saying it
Why
too.
not is what we are adding to R
And
times.
then wow,
So if all the y nots are 0,
and
and then the R that we're using to multiply the other aspects are 0, then 0 plus 0 is 0. All of them will be 0.
Okay, let's see. What's our normal equation?
y, plus r,
Okay.
y is not 0.
So, b is what is increasing. So we're still going to have our 0, 0, right? 0, 0 here, 0, 0 here. So get our 0, 0, right? So what is it going to be? What's our y 0?
0.
Okay. Our r is what?
0.
0. Our y 1,
0.
y 0.
0.
What is it going to give us?
0.
That's my question, right? For 0, 1, what is it going to be? That's still 0, right? For 1, 0, where is this 1, 0? 1, 0. Mm-hmm. Into, which is what? Okay. For 1, 1. So we basically got clap for yourself. Okay.
For 1, 0, 3.
So let me clap for you because you people are the ones that predicted it out. So I'll clap for you people, don't worry. Okay, so good. You guys got it right. How about when we are evaluating at b equal to 1?
0, 3, 2, 5.
0,
3, 2, 5.
3, 2, 5. Interesting. Is it true? Eh, don't trust, verify, Abby. Okay. Okay, let me change this one to 1, Abby. Oh. But is it okay now? That's so much. Okay. So I'm changing it to 1. What is it going to give us?
0, 3, 2, 5.
O'Shea. O'Shea. Okay, nice. So B at 1 will give us 0, 3, 2, 5. Right? Was there any need for us to evaluate? No need, right?
Yeah, actually.
We just picked values from our definition and we got it. How about if we, okay, so if I tell you evaluate at a equal to 0 and sum over the Boolean hypercube,
Just pick
Just pick the first half.
Pick the first half and the second half.
No, that's the
No.
first half.
I say evaluate at a equal to 0 and sum over the Boolean hypercube.
And some over the blind.
The first half for me.
First half and add them together.
Is that true?
Yes.
Is that true?
You come again with the question.
Don't find out.
Let's find
So
out.
what's the question again?
Are we finding out again?
No.
So if I say evaluate at a equal to 0 and sum over the Boolean hypercube,
That is it. Like,
So that's the first half.
that's the point where a equals 0, and so we are just picking the first half of the whole array that we have, and the sum of it just gives us the
Question is, what do you mean by the sum provide the just addition?
sum is addition, right? So we're saying like evaluate it over the Boolean hypercube and then sum the results. Yeah. But you know, like
That's the sum of the first time.
that is sum of the first half, right? Or if I say evaluate it at b equal to 1 and sum over the Boolean hypercube.
First time. B equals to 1.
Yes.
That's at 11, 2, 3, and 7, and 6 and 7. Then something.
Right? Which is basically where b is equal to 1. Here, 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 here. Right? And then we sum them. Right? So does this make sense up to this point? Are we sure? Are we sure? Sure? Okay. So this same polynomial, if we want to evaluate it at b, okay, let's say we want to evaluate it at a equal to 2. Huh? Oh, we will. We will. The verifier's randomness. So the verifier's randomness that is going to take us out of the here. So does that make sense? So if we want to evaluate at b equal to 2, how is it going to look like? Are we still picking values? Huh? Can we?
at b equals to 2.
Yes, we want to evaluate at b equal to 2.
You use this formula now.
You just
Still this
add-
formula,
add
right?
it just
How
to-
would it go?
Then you just do everything.
Yeah, it's the same way for Aries.
Yeah. But like now we need to calculate,
Yeah.
right? Initially we did not need to calculate because
I think
we already had that. So once we get out of
0 and 1.
here, we need to now calculate. Right? So at b equal to 2, say 0 what?
6, 4, 4,
4.
Yes, 10.
That makes sense. So is this the evaluation over the Boolean hypercube of the new polynomial we will get when we evaluate? I'm gonna question a lot. Okay.
So, yeah. So is it fine to say that evaluating at any point, like say b equals to 2, b equals to 5, we just resort to getting the evaluation of b at 1, then plus the evaluation of that point times b at 1. Like getting the evaluation of b at 0, then the product of that point, that value times b at 1.
I think
B at 0. Like,
is it not this
if you
equation
say- if
you're
you say-
still trying
yeah,
to
like if you say evaluating over at b equals to 5, we will easily say evaluation at b equals to 0 is 0. Evaluation at b equals to 1 is an array or whatever it is, or that value that it is. Then evaluation of b at 5, since we have that listing, will just be that initial b at 0 plus 2 into like b equals evaluation at b equals
is it not this formula
2
here?
into this. Yeah, something like this. Like I'm not looking at the array. Like if you want to sum it up, like we have to now start calculating on with that kind of formula so nice.
I don't know if I got you, but you need to actually do like this. Like you need to interpolate and evaluate.
I was
Right.
even thinking that you would say that if we want to, for example, evaluate b equals to 5, are we going to multiply 5 to the array of 2 equals
That's
to
what I
1?
just said.
Is that what you meant?
Yeah, that's what I just said. But then you can't forget b equals to 0.
No, we can forget because it does not really.
That's because b is 0 now.
Yeah.
What if in that
So now,
sense
that
it's not 0?
you are answering your question now.
And that's what I'm saying. No, that's my question. My question is it right to use that kind of calculation, or is it possible that that calculation might be wrong and we just have to just do this? That is external of 0 and 1. We just have to just calculate all the points and stuff.
This example is just like that. It's just a special case. When you give yourself another polynomial and you do it, you will not be consistent.
Say what?
Yeah.
Let me
Huh?
see. It's basically associativity, right? It's basically associativity. Like if I'm getting your question,
I don't
well,
think you get your discussion.
I think it's getting it now.
Okay.
I think so.
so you're saying we already have these values, right? This one,
Yes.
right?
Yes.
And we have this one.
Yes.
So maybe if we want to evaluate
Any point.
at any point,
Yes.
it's just to do this times this value plus y at 0.
Exactly my point.
Is it now? It's still the same thing with this. That is what I was trying to say. It's still the same thing with this. But it's not every time we are going to be using like for Sumcheck, right? For what we are doing now, we are working with y evaluation at y at 0 and y at 1. You get? But a straight line, you can use 2 points. You can use y at 5 and y at 9. Right? In that situation, like y at 5, you can still think of it as y at 0 because that's like the starting point, right? Then y at 9, you can think of it as the ending point.
Oh, like well, okay. I was actually thinking maybe if they just said like why at 5. You know, like why I came up with why I thought about that is, you know, we have the Boolean the evaluation over the Boolean hypercube already. So like taking A for instance, which is very easy, you know, stuff like that. So even if they say A at 15, we could actually just, for instance, we could actually just say, okay, give me the first values, the sum of the first values of the sum of the half of the first values of A, then plus that 15 in times the sum of the last values of A, just to make the computation just round up.
Faster.
Just think.
Yeah.
But I get your point of two different.
Two
like,
different.
starting points.
And the ending point, right? In that case, like, it will be y of 5 plus r times this,
Yes.
right?
My-
But it's still like a straight line. Okay, so we said, who should listen or if you are not listening before? We said when we evaluate at b equal to 2, we are going to get this, right? Right? Now let's look at our own original polynomial in coefficient form, right? Our original polynomial in coefficient form was 2ab plus 3bc, right? I want to evaluate at b equal to 2. I want to partially evaluate, sorry. I'm always this thing. So what is that going to be? That's going to be 2a, right? Plus 2c, which is 4a plus 6c, right? This now is the coefficient form. I want to evaluate this polynomial over the Boolean hypercube as 0, 0 for a and c, 0, 1, 1, 0, 1, 1. This will be 4. What is it going to be? 0, right? This will be 4, which will be, this will be 4, which will be,
That should be one.
oh, sorry. Right?
Wow.
Is this the same thing?
Yeah.
Right? It's the same thing, right? So, we said there are two ways of representing a polynomial. In the coefficient form and in the evaluation form. So when we are talking of this, do we still mean this?
Yeah.
If we are talking of
This array? Say we do not know the polynomial in the coefficient form, right? And I just showed you this array, like 0, 6, 4, 10. Am I still talking of 4a plus 6c?
yes.
I'm still talking of 4a plus 6c, right?
Yes.
It might be possible, I'm not totally but it's possible I do from evaluation form.
From evaluation form to coefficient. That will now require you to interpolate. Right? That will require you to interpolate. And when you interpolate, since basically you're going to now relabel C to B. Is it making sense? Are we sure? So,
Sorry. A univariate polynomial will always have two elements in the array.
yes.
Yeah, that's all.
Okay. Okay, so let's go down again, right? We've evaluated at b equal to 2.
Is it a univariate polynomial will always have two elements together?
Yes, now.
No, not all, sorry.
What about
Yeah.
the ones with
Not
power?
all univariates. It depends on the degree.
Okay, not all univariate.
So we're talking about
But-
the ones, the power
but-
of one
This, the univariate we are going to get
from a linear.
from this multilinear polynomial will always have two elements in the array.
Yes, because it's a linear.
Next univariate.
Which is the evaluation of that polynomial at 0 and the evaluation of that polynomial at 1. Does it make sense? It's going to have 2 points. The one we are going to get, you get, is going to have 2 points, which is the evaluation at 0 and the evaluation at 1.
Okay.
So we've evaluated at b equal to 2, right? Let's evaluate at a, or let's partially evaluate, sorry, at a equal to what?
5.
At a equal to 5. We don't know this guy. We're still working with our evaluation form, right?
Honestly, the evaluation at a equals to b equals to
2.
2 and a equals to 5 has to be confusing because I'm understanding the evaluation, but I'm trying to figure out why it's useful in the sum check. Yes, because like the sum check we are never going to evaluate at 5 and this unless maybe when we want to partial evaluate after we have gotten the randomness. But that other evaluation where we are trying to evaluate 2 variables keeping 1, or where we are trying to keep 1 variable, for instance, we are never going to use like 2 or 5. So I'm trying to like think of like the reason why we are evaluating a equals to 5 and b equals to 2. Like
Okay, no. This is just, yeah. So I want us to just go down to that univariate polynomial we were asking, so that we'll see what it will look like, right? I also wanted to go down to like the univariate polynomial in this representation. What is it going to look like? You get? So, but we understand up to this point. Sure? 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 Where are we lost? Huh?
Spider, my excuses, right?
Huh?
Spider.
Sorry, where did we get lost? Huh?
Follows when you got the other representation.
Okay, so you got how we got 0, 6, 4, 10.
Yes.
Are you sure? What did we evaluate the polynomial at?
D, when B is equal to 2.
When b is equal to 2.
Yeah.
Are you sure? It's not when a is equal to 5. Eh? When b was equal to 2. Alpha. Michael, right?
Spider.
Alpha.
I think I'm not doing everything physically, but as you're evaluating this calculus, I understand that way.
Well, like, is there any question you can ask that can help us bring you back? Like,
Like, how this is when you're trying to
understand it. No? Ask. Mitch.
Yes.
Ask.
All this stuff that they are doing now, I want to really subject. It's not like what I think
Yeah, because like it seems a lot of people were getting it. Like
Because like we went back to the
yes,
very beginning of the week, like 3 weeks back.
yeah.
You know, like, are we, is it because of the Sumcheck we are doing this, or what doesn't just do revision?
It's basically because of Sumcheck. Yes, because of Sumcheck. Because
There's a way this one directly affects Sumcheck.
yes,
Directly, indirectly.
directly,
Directly.
implementation wise. So that's why we should be paying attention because like this affects Sumcheck implementation wise. If you don't understand this, your Sumcheck protocol will be so complicated. Like you're just going to complicate your implementation. Not like so complicated, but you'll be doing a lot of unnecessary things. Does it make sense? So I'm trying to make us understand why we even decided to tell you people to forget about sparse representation and dense representation and just implement evaluation form. There was a reason because of Sumcheck, so that you guys don't do some work that you're not supposed to do. But is everything making sense up to this point?
Yes.
Is it? Sure. The both of you. It is, right? Favor. It is. Israel. It is. Superman. It is.
Spider.
Okay. It is, right?
I'm waiting.
Gradually. Okay. So let's evaluate this polynomial at. We said a equal to 5, right? How are we going to pair it? Want to evaluate this polynomial? Forget about this guy. You know, we're still working with evaluation form. You get. So, want to evaluate it at a equal to 5 using our normal linear interpolate and evaluate function. How are we going to pair it? 0, 0. We're pairing it with what? With 1, 0. Right? Then,
Is it 2 variable?
yeah, 2 variable. This is 2 variable. 0, 1 to 1, 1. Right? So 0, 0 is 0 to 4, 6 to 10. Right? What's that formula again? Okay. So when we do this, we are going to get the evaluation at 0, right? And 1, right? The new polynomial we are going to get, we have 2 points. So we are going to get the evaluation of that new polynomial at 0 and 1.
Okay, so we are evaluating the next set that the first one we got from evaluating at
Yeah, B.
So
Wow,
partially
yes, we're
evaluating.
partially evaluating again. So now get the univariate polynomial. Does it make sense? So this is going to be what's our y0 for
0,
0 plus
0,
our
Five.
A is 5, which is like our R, right? Into what? 4 minus 0, which is 20, right? What would this one be? 10 minus what?
6,
That's 6 plus, what is this? 4, right? 5 times 4, 20. So 26, right? So we're basically getting a new array, 20 and 26, right? This is a new polynomial, right? In how many variables? In one variable, right? So now let's get the coefficient form. Let's work with the coefficient form and see if we still get this. What was that coefficient form? We removed it, right? It was 4a plus 6c, right? Do you remember how we got 4a plus 6c?
That is evaluating B equals to 2.
Yes, evaluating the original polynomial at b equal to 2. We now got 4a plus 6c. That's coefficient form, right? So 4a plus 6c, I want to evaluate at a is equal to 5, right? That will be 20 plus 6c, right? If we evaluate it at 0, what are we going to get?
26.
Right? If we evaluate it at 1, what are we going to get? So, say we just had these values. Does it still mean 20 plus 6c? It means, right? The both of them are the same. It's the same polynomial, just represented in different ways. So we've been doing the sum check over the coefficient form, but it's just a representation. Same thing still applies in the evaluation form, right? But now we're working with just the evaluation forms of the polynomial. Anything we get, if we interpolate, we're still going to get the coefficient form. You get? But the idea of multilinear polynomial is that interpolation process is costly, and we want to avoid that interpolation process by all means. You get? In the univariate case, I think there is a way like a barycentric evaluation, right, that can be used for the univariate case. But in the industry, like, they can't, in the industry, protocols working with univariate polynomials, they can't avoid interpolation. That's why we have FFT. FFT just helps to reduce the interpolation cost. So instead of the interpolation process to be, I think, n squared, FFT reduces it to n log n. So, like, in the multilinear case, we don't even need to do interpolation, since we know these things are straight lines. Does that make sense?
Yeah. So evaluation is not expensive.
Huh?
Evaluation is not expensive.
Evaluation is expensive. In what sense, though?
No, like as you said, we are trying to avoid interpolation because it's expensive.
Yeah.
So like,
Evaluation, we're always going to evaluate.
you can't avoid it. You can't, like there's no cheat code to
The
it.
verifier has to evaluate at a random point. So we can't evaluate. Barycentric evaluation enables like evaluating over the evaluation form of the univariate, right? But aside that, if you have like just the evaluation form in a univariate polynomial, you need to interpolate to get the coefficient form so that you can now evaluate it at any point. That would have still been the same case in the multilinear case, but or in the multivariate case, right? But because we are dealing with multilinear, there is no need for that. If we enter multivariate, then that I interpolate and evaluate function is now going to be more complex. Well, let me not go into that part. Let's not go there for now. But do we now understand that even if we are doing this thing in the evaluation form, it's still equivalent to doing it in the coefficient form?
Yes.
That makes sense,
Yes.
right? Okay. So Cass, the question you had, have you somehow gotten a listen of the answer?
Yeah, basically, what I'm thinking about the process is looking. So, already we have where we are giving the stuff in evaluation form, right? We already have the values. We already have the values because those values were actually evaluated over the peculiar hierarchy. Now, if you split them into zeros and ones, that array is going to split into two. Yeah, so if the array is split into two,
Okay, let me just say,
so it looks easier when you're evaluating at A. Okay, you can't evaluate at A again. You can't. It looks easier when you're evaluating at A. That means once you've evaluated at A, the next time you're coming, there's no A again.
yeah, there's no A again.
There's no A again. It's just B.
B and C.
Are you coming with this?
Okay, eh? You say?
Can you explain it?
Okay, the question.
Yes.
So the question was like, how can we skip one and sum over the Boolean hypercube without actually evaluating the polynomial over, like, without doing like a for loop where you now have to start evaluating it over all possible combinations of 0 and 1. Do you have an idea?
If you don't want to, maybe you have to like
So-
change to one thing.
So, how many this time?
How can we in code? How can we skip one and sum over the Boolean hypercube?
Before we get to the code, but I'm still also confused.
Of the axe.
Since we are about let's say we're working with ABC and three variables. Like evaluating both B and C.
Hmm?
To get the numerator for evaluating both B
And
and C.
both B and C, yes.
So
It's still. Don't worry, it will make sense now.
So,
I'll ask one question, and I hope that question will help.
so
Wait, let him. Sorry. Yes,
I should ask.
yes.
Okay, so yesterday when we were looking at, can you write that 2AB plus 3BC? Yeah, so at first we
Sorry, please, let me be sure this thing is okay.
so if we evaluate this
My battery.
polynomial at
Okay, I'll plug it.
we are skipping A and we are evaluating at B and C, right? We are
Yeah.
going to get 2A.
Yeah.
Yeah,
So
just
let me
like
be
this,
writing
right?
it. Right. So we're skipping A,
Yes.
and we're evaluating at B and C.
No, just write the answer. I've done that.
Okay, you've done
Just
this
you are
one.
going to
So
get 2A. Then the next one will be plus 6A plus 2. So this is going to give us 8A plus 2. Now, if we evaluate at 0 and 1, we are going to get 10.
this, so right.
Yes.
Right.
We are
Yes.
going to get 10.
Yes.
Now, this 10 that we have gotten, right?
Yeah.
If you go back up,
You did not say 10. You are looking
no,
for
no,
10.
just go back up.
Okay.
No, sorry, it's not supposed to be 2 comma. It's not supposed to be 2 comma 10. It's supposed to be 2 comma 8.
Is it 2 comma 8?
It's like we didn't get the polynomial right. It's supposed to be 2 comma 8.
Is it 2 comma 8?
Is it 2AB plus 3BC?
That is 4.
Huh?
Is that no?
Wait. Okay. Let's actually do it.
Yeah,
Right.
2
Let's do it.
But the equation is correct.
Yeah. So this will be A 00, A01, A10, A11, right? So this will be 2A this, right? So be 2A this, right?
Yeah.
This will be 2A
Yeah. 1. That's so that's 2A.
this will be
2A.
right. So summing it will have
Okay, so let's evaluate at 0 and 1.
right. Right.
This is not the question we use. I think there's I've missed the question.
You know that day we saw the different polynomial.
Yeah,
Somebody
it's
gave
not the
a
polynomial
random.
we use.
There was 10 there also. There was 10 in that polynomial.
Which was one? That was mine.
Yeah, that will.
Huh? That polynomial is there.
Which polynomial?
10AC plus 2BC plus 5A.
That depends on
Okay, let me see.
Yeah.
Let's see.
I shall know the ended
Just
Let's scroll down. No, this is not what I'm talking about. Scroll down.
The other one.
The one we just wrote. Let me check
Okay.
something. Okay, it's supposed to be 3AB plus 2BC.
3.
AB plus 2BC.
Okay, 3AB plus
Yes,
2BC.
plus 2BC. Plus 2BC. So
Okay.
let's just wipe this guy and we'll solve this guy. It's supposed to give us 2, 8.
Okay, I just buy this guy. Three AB plus 2BC. Right?
Alright, slide it. Okay, off now. Yeah.
Okay. Right. That's up.
Okay, it's here.
Okay.
I show you.
Okay. So that's 2. That's 3A plus 2.
Yeah.
Right.
Yes.
There's 6A
Plus 2.
plus 2.
Yeah. So it's evaluate as well. So, 2, 8, right?
Yeah.
Alright. So if we go to that.
Oh, it has not come.
Huh? Okay.
Oh, it has not come. Okay, well, I'm with you.
Yeah, so if you go to that, I think this was the same polynomial you used at the first instance. Like the top,
No.
this was the polynomial.
Yeah, it was 2A plus
Okay. So if we
2A plus 3
if
basically.
we run this polynomial over the Boolean hypercube and we separate it into zeros and one, we are going to see that when we sum them together, we are still going to get 2 and 8 in it. So, but the thing is, it's not really adding up in my head. I can see 2,8 here, but if I add it up there, I still see 2,8. Just that there are extra zeros in each of them. So,
Okay. So,
like if you evaluate this polynomial now, this where is it, the 3AB plus 2BC over the Boolean hypercube. If you
okay, the complete one, right?
Yes, the complete one.
Okay, let's do that. 3AB plus 2BC. Right?
0,
right?
Right. So if we if we separate it, like let's take 0002 and add it to 0035 on it.
Right?
Yeah.
Right?
Yeah.
Are we following? It's a lie. It's a lie. We are not following. Are we sure?
So if we sum these guys,
Okay.
we sum everything on this guy,
If we sum everything where?
on the a equals to 0,
Okay.
we are getting 2. And we sum everything on the a equals to 1, we are getting 8. Can you see it? And this is the same with the
Wait,
2,
I cannot
8.
see it. Wait. Okay, I can see it.
See now, if we sum everything here,
Yes.
we are getting 2. If we sum everything here, we are getting 8, which is the same thing to the 2,8 we had the other way. Is this it?
What does that mean? What does that mean? You've gotten it, but what does it mean?
So, if we sum everything on a equals to 0, we are, that's when a is 0 now. Like, we,
You need 2 points to represent a straight line. Right?
yeah.
Okay, so let me ask that question I wanted to ask. We're trying to generate, we have a polynomial, right? And we want to generate a univariate polynomial from that polynomial, right? We have a polynomial, what is this polynomial again? 3ab plus 2bc. (3ab plus 2bc). I want to generate a univariate polynomial from this polynomial. To get a univariate polynomial from this polynomial, or to get a straight line from this polynomial, so we want to get a univariate polynomial in A, right? F of A. How many points do we need to represent a straight line? 2 points, right? What 2 points can we use? No.
Okay, 0 and 1.
We can use 0 and 1, right? Okay. So we want to generate a univariate polynomial from this, and we need 2 points, right? Let's evaluate this at f of a. Okay. Right. That's still basically like the sum over the Boolean hypercube, right? Because we are evaluating it at a. What happened? Right. Right. So we are keeping a and we're evaluating the others over the Boolean hypercube.
Yeah.
Right. But technically, if we say we want to get a polynomial f of a, we need 2 points. We need where a is 0, right?
And where A is 1.
To get the polynomial where, like, we need 2 points to form a straight line where a is equal to 0 and where a is equal to 1, right? So to get the polynomial where a is equal to 0, we take all the places where a is 0, right? Which is 0, 0, 0, 2. Right. This in itself is f oh, it's not showing. So this in itself is f of a, right? Where if we put like f of a equal to 0, it's going to collapse this. So 1 point, right? And this in itself is still f of a, right? This is 0, 0, 3, 5.
Alright, so what?
Wait, sorry, this where a is 1.
So now that's equation 3ab plus 2bc, right? Let's say we sample a random challenge at 10 and evaluate a at 10. I don't know if I just, let's say we sample a random challenge and evaluate a at 10.
If we evaluate, this is where a is evaluated as 0.
Yes.
That's what gives us this point,
Yes.
right?
And we have our univariate polynomial, which will be committed.
We can basically, you already said it, right? That is the sum of this,
Yes.
right?
So I'm trying to go like, okay, now we have gotten our univariate polynomial, which you can send to Fiat Shamia to commit, right? We get a random challenge, right? Which that random challenge now we are going to use the value to substitute a in the original polynomial. That's the first polynomial. right?
Yeah.
So once we do that, A is no longer there. So the next level of univariate polynomial we are going to do will now leave us with just B and C.
Yeah.
So we are still going to repeat this process again, splitting it into 2 again, getting B and for 0 and getting B for 1 again. This same stuff we just did here. So that way we get our B.
But it has not ended here.
Yeah.
We're still going to do the sum now. We need the points. It's only, you can use just 2 points to represent a straight line.
We have
Right.
done the sum now that we got 2 from
Yeah,
it.
which is that sum, 2,
Yes.
8. So this is the evaluation at 0, right?
Yes.
At a equal to 0.
Yes.
And this is the evaluation at a equal to 1. So this is like that straight line, which is similar to this one. Where was that?
Up. I think it's up.
Okay, which is similar to this one.
Yes. So this is what we are going to commit. We are going to send to Fiat
Yes,
Shamia
this
to
univariate
commit.
polynomial.
Yes.
Yes.
Now once we send this to Fiat Shamia, we are going to get a random challenge.
Yes.
When that random challenge comes, we are going to use it to substitute A in the original polynomial.
Yeah.
So that's where we are going to partial evaluate A at that
That random challenge.
challenge. Now once we do that, it's going to reduce that polynomial by half,
Yeah.
right? Which means A is no longer there. We are now left with B and
With
C.
B and C.
Now, once we are left with B and C, we are still going to split this same thing we did for A. You know, we are now left with 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, which means B will be 0, B will be 1. So if we split it again, we are still going to get the half for
Half.
B0, sum it up, get the half for B1, sum it up. So that's how we are going to repeat the process.
Does this, like,
Yeah,
it's clear.
now.
Is there any need to evaluate?
Yeah.
No need.
But is
Right.
the transcript getting just the array or is it getting like the sum again? Like to absorb and trace?
The transcripts. Is it getting the
You know, like you have the variance polynomial. Then you also have a claimed sum.
yeah?
We are sending the two to the actual.
So the transcripts, yes. But does this make sense? It makes sense. Perfect. Also, we've gotten this polynomial. This is the univariate polynomial in A, right? Right? If we evaluate this polynomial at A equal to 5, right? What are we going to get? That will be this are y0, right? This are y1. So that will be 2 plus 5, right? Five minus 2, that's 6, right? That's 30, right? We agree, right? This is the univariate polynomial. That we evaluated at R at A equal to 5. Right? If we now evaluate this original polynomial, where's that polynomial? 3A plus 2BC. 3AB, sorry, plus 2BC at A equal to 5. right? We are going to get, let's do it in the evaluation form, right? 0, 0, 0, 0, 0, 0. And you need to do it in the evaluation form. Let's just do it in the coefficient form. So that will be 3. Right? This is the polynomial we get, so we now partially evaluate at A. So if we evaluate this guy over the Boolean hypercube, this will be 15, zero, right? Zero, right? Are we together? 15, right? It's what? Right. The both of them are equal. So basically with this we can see that the verifier on the verifier's own can generate the claimed sum, right? By evaluating that univariate polynomial at the random challenge. Does that make sense? The program generated the univariate polynomial, right? Sent it to the verifier. The verifier evaluated it at 0 and 1, summed it together, and checked if it was equal to that previous claimed sum, right? If it's equal, the verifier says okay, right? Samples a random challenge and sends it to the prover for the prover to generate this polynomial, right? Okay. So for the prover to evaluate the polynomial at that random challenge, right, to get this polynomial, right? And then the prover now needs to generate another claimed sum, right? That is the evaluation of this new polynomial over the Boolean hypercube. You get? But basically this polynomial was gotten by skipping A and summing over the Boolean hypercube, right? So if we evaluate this polynomial at a random point, we should get this new polynomial already summed over the Boolean hypercube. Does that make sense? Huh? Okay. So the verifier, after doing the check, right, the prover sends a polynomial and a claimed sum. That is the evaluation of that polynomial over the Boolean hypercube, right? And the prover generates a univariate polynomial, right? so that the verifier can evaluate that univariate polynomial at 0 and 1 and add it together and check if the result he got is equal to the claimed sum that the prover sent. Right? Is that clear? Sure. So, after the verifier has added them together and checked, if they are equal, the verifier then samples a random challenge and sends it to the prover. So evaluate that initial polynomial at that random challenge to get a new polynomial, right? Which is this polynomial here. Right? Just evaluate that initial polynomial at the random challenge to get this new polynomial. Then the prover is expected to sum this new polynomial over the Boolean hypercube to get a new claimed sum, right? So we have reduced the original Sumcheck in, let's say, 3 variables. So a new Sumcheck problem in 2 variables, right? But this claimed sum, the verifier can get this claimed sum by the verifier self. How? We remember that the prover sent this univariate polynomial that the verifier had to evaluate at 0 and 1 to get the first half and the second half, right? So after evaluating that polynomial at 0 and 1 and adding it to get the previous claimed sum, now we are now talking of how can the verifier get the new claimed sum, right? This new claimed sum for the next round. You know, after the prover does this, he reduces that initial Sumcheck problem, the Sumcheck problem of 3ab plus 2bc over the Boolean hypercube. After evaluating this 3ab at 2bc at 5, he now reduces that problem to the sum of 15b plus 2bc over the Boolean hypercube, right, for the next round of the Sumcheck protocol. Well, with this polynomial, which is the f of a polynomial, if the verifier evaluates, we can remember this, right? This is basically the sum over the Boolean hypercube in b and c. That's what gave us this 2. This is the sum over the Boolean hypercube of b and c when we evaluate at 1. That's what gave us this 8, right? Which is basically what the verifier, or basically what the prover is now trying to like do again. But now the verifier is using like a different approach. He has this sum over the Boolean hypercube for this a at 0 and at a at 1. So for him to get that claimed sum that the prover is supposed to get when the prover evaluates at r, all he needs to do is evaluate this polynomial at a equal to r.
So it doesn't need to use the univariate.
No, this is the univariate that was sent. I think
I want to understand something. So the thing is, we have the verifier, we have the prover. So now the prover has given, the verifier has given the prover a random challenge to evaluate. Let's say at the second step, since it's going to be 2 variables, b and c. So the prover will now come with a claim sum that he has done it, but the verifier also wants to do his own check to get the value. So what he's going to do is he's going to substitute it, since he has the first original polynomial that was given, which was evaluated at zeros and ones, and he has a, so he will substitute it at, and he'll be able to get the same value for the first polynomial to be equal to the claim sum that the prover has given him
That the provider is going to give him on the next
on
round.
the next round.
I don't know if that makes sense. We're not looking like it makes sense. Okay. So we have a univariate polynomial, and the provider is trying to prove the sum over the Boolean hypercube, right? It sums that polynomial over the Boolean hypercube. So that is the sum of the polynomial over the Boolean hypercube for that initial polynomial, right? We now want to reduce that problem to still a sum check problem, which is the sum of a new polynomial over the Boolean hypercube, but in smaller number of variables.
Can we use that 0.0030335
Okay. That's 2ab plus 3bc. Right. Okay, so okay, let's
the evaluation
the evaluation form. This is 0 0 0 3 0 0 2 5. Right. So to generate the univariate polynomial, what do? We partially evaluate at, like, we skip A, right? Then partially evaluate at B and C and sum over the Boolean hypercube, right? So that's basically right, the evaluation at 0, the evaluation at 1 of the new polynomial f of A. Does this make sense?
Yeah.
Which will give us
The function we have for evaluate and calculate cannot be used for this part.
you don't need to use it. You can use it, right?
But then we have to do like twice because we are evaluating two variables, leaving just one.
Yeah. You do it for, because now you'll be pairing, right? So you just call partial evaluate since you've implemented it already. You get. You can just call partial evaluate at 0, right? A partial evaluate at 1. Then you sum it to get this. Partial evaluate at 0 will give us this, right? Partial evaluate at 1 will give us this. When we sum it, we get 3 and 7. Right? So this is a new univariate polynomial in A. Right? And this is what the prover sends to the verifier. The sum of this was 10. Right? The sum over the Boolean hypercube was 10. So the prover generates this univariate polynomial, sends it to the verifier, right? The verifier evaluates this polynomial at 0, which is just 3. So the verifier just technically calls dot sum on this array, right? To get 10 and checks. That is, checks if the evaluation at 0 plus the evaluation at 1 is equal to claimed sum. right? Is it making sense? Are we sure? Sure? Jude, is it making sense? Okay. So, after the verifier has done this, the verifier samples a random challenge, right?
That's some got it then. There's the approval that you do.
This one,
Some got it then. Yes.
yeah, it's the prover that did it. So that's what the prover is trying to prove, that the sum of this polynomial over the Boolean hypercube is this.
So at first, you evaluate that over the hypercube.
Over the hypercube.
And get a sum.
Yes, and that is sum.
So
Yeah.
these 3 and 7 now. I thought you're supposed to return.
He now generates a univariate polynomial in A.
So after doing this first step,
Yeah,
he generates this
univariate
by
polynomial
evaluating at A, abi?
by skipping A,
Skipping A and evaluating B and C.
C over
Okay,
the
then you now
hypercube.
send that univariate and then the sum to the verifier.
Yes.
Is it not the verifier that will do the sum at 0 and 1?
There is
No,
a
he's
trade-off.
sending this initial. This is what he's trying to claim, that this polynomial
Okay, yeah.
evaluated over the Boolean hypercube
Then
is this.
you will not
You now
get the
partially evaluate
univariate.
at B and C. You now get F of A.
Okay,
Yeah,
You
which
now
is
send
this.
it together with that sum that you got.
And
So the
send it
verifier will
together
do
with this.
0 and 1.
Yes,
Yeah, so that the verifier will evaluate at 0 and 1. And make sure that it's equal to the claimed sum.
Yeah,
You get.
yes.
So if it's equal, the verifier will now sample a random challenge. Right? Right?
Yes.
And send it to the prover. The prover is now expected to evaluate this polynomial at that random challenge to get a new polynomial. Right? You'll get 2 variables. That's what's basically trying to reduce that initial Sumcheck problem over 3 variables to a new Sumcheck problem over 2 variables. Right?
Yes.
So he evaluates. We're still trying to get the new Sumcheck problem. Right? We're still trying to get the new Sumcheck problem. So to get that new Sumcheck problem, the prover evaluates this original polynomial at the random challenge to get the new polynomial. Right? Which is
Sorry. This supposing now we are sending this 3 and 7 to the verifier, meaning that this 3 and 7 is supposed to be like the variance.
yeah, the univariate polynomial in evaluation form.
Meaning 3 will be
Evaluation of that univariate polynomial at 0. And 7 is the evaluation of that univariate polynomial at 1. You get it? So the verifier doesn't need to evaluate again, just sum. You get it? A lot of people will be thinking of how they will now start evaluating the polynomial over the Boolean hypercube, how they will start generating the evaluation points to pass into the, but we get the picture.
But the evaluations are already there.
The evaluations are there. Exactly.
Where does the array that we get when we substitute a now
The array will get
before the array of
like this initial array.
not the initial array. You know when we evaluate this array at A equals to at A, we get an array of 4 elements.
Yeah, when we now sum, that is basically when we now sum them. You know, we say when A is equal to 0, that will give us that first half. So we need all the places where A is equal to 0. So we sum them up to get this point where A is equal to 0.
I get how we are getting this f of A equals to 3. So one question, you know, when we evaluate A at 0 and 1, we are meant to get an array of 4.
Okay. When we have not gotten to that point. That is when we evaluate. Are you saying when we evaluate A at the random challenge, we are now meant to get a new array? No, we have not gotten to that. That is what we are now trying to do here. You get?
So what we are doing in essence is 4 to get it, but give that one to the verifier, check it out for the sum.
I think you're confusing it now. When we skip A and sum B and C over the Boolean hypercube, we are going to get a univariate polynomial, which is 2 points. We send that univariate polynomial to the verifier. The verifier evaluates it as 0 and 1 and checks if it equals to the claimed sum. Right? If it's equal to the claimed sum, the verifier now samples a random challenge. Sends that random challenge to the prober to evaluate this polynomial at the random challenge. That's what we're trying to do here. When we evaluate this polynomial at that random challenge, that's when we are going to get the new polynomial over 2 variables, which is 4 points.
So we are not sending the polynomial to the verifier, we are not sending the sum.
Which of the polynomial again? We are sending this univariate polynomial to the verifier.
The 3,
Yes, this 3,7, which is a univariate polynomial. The idea is a univariate polynomial in A, not 3,7. Forget 3,7. We are sending a univariate polynomial in A to the verifier. Right? So that the verifier can now evaluate that univariate polynomial at 0 and 1 and check if it's equal to this original claimed sum. So if it's equal, that is when the verifier starts talking of generating a random challenge. Right? And we have said let the random challenge be 5. If the prover then evaluates this original polynomial, which is this, at r equal to 5, we are now going to get a new polynomial in 2 variables. So we are basically now trying to reduce that Sumcheck problem into a new Sumcheck problem over this new polynomial in 2 variables. Let's just be following us. What I think when we expand this, maybe your question will be answered. So this is, we're going to do it in coefficient form and then evaluate it over the Boolean hypercube, right? So that can just be straightforward. So this is 5 plus 3 BC, right? Which is 10B plus 3 BC, right? So after the prover evaluates this polynomial, it's going to get a new polynomial, which is this. In evaluation form, this polynomial is going to be a 0, 0. This will be 0, right? This will be a 0, 1. It will still be 0. A 1, 0. It will be 10, right? A 1, 1. It will be 13. This is a 4 you were talking about, is it? Are you sure it's this one you were talking about? Like, this is what we are going to get. Yes. Yeah. But it's still the same thing as this one. Yeah, that's what I'm driving at. Perspective. Okay. Okay. So we have reduced the problem from the sum of a polynomial in 3 variables over the Boolean hypercube to a sum of the polynomial in two variables over the Boolean hypercube. That means we need a claimed sum for this new polynomial, right? And to get the claimed sum for this new polynomial, the prover evaluates this polynomial over the Boolean hypercube and sums it. What is that going to be? 23, right? So the new claimed sum will be 23, right? So we now need to perform like the Sumcheck protocol to prove this. You're claiming the evaluation of this new polynomial over the Boolean hypercube is 23, right? So the prover now needs to generate another univariate polynomial, f of b now.
Oh, sorry, is the prover sending the claim sum?
This claimed sum
The array of this, polynomial
to the verifier. That is the claimed.
just the claim sum.
The prover doesn't even need to send, the claimed sum. Right? The only claimed sum the prover needs to send is
In the first one.
this first one. Why? Because the verifier can generate this claimed. The verifier can generate this claimed sum by the verifier self.
I thought you wanted to like compare if
Yeah, he's still going to. He can generate it by himself, and then that's for the next round now. Right? I'm going to explain that. But we get up to this point, right? So we have reduced the Sumcheck problem from a polynomial in 3 variables to a polynomial in 2 variables, right? Good. So, in order for the prover to prove this, the prover now needs to generate a new univariate polynomial in f of b, right? So that they will now repeat this process. The verifier checks this plus this if it's equal to this claimed sum, right? And if it's equal, the verifier samples a new random challenge, right? And then sends that random challenge to the prover. All that one makes sense, right? By just repeating what we've done. So now let's talk about how the verifier can get this claimed sum even without the prover sending it. Does that make sense? The verifier does not even know this new polynomial, right? So how can he get the claimed sum without the prover sending it?
wait, the verifier doesn't know this polynomial. I thought the prover was supposed to send it.
What the prover sends to the verifier is just like there is a certain polynomial, and you say the sum is this.
How do we now
Sorry,
confirm that the evaluation is true?
Wait,
If
the
I
verifier
don't know the
doesn't.
polynomial.
Sorry, I thought you were supposed to send the univariate polynomial as
And
well.
the claim
Yeah, this univariate polynomial f of a,
Eh?
right? Is this univariate polynomial f of a now
Yeah, that one we're sending with the sum now.
with the sum?
Said we
Yeah.
Yeah, I know you say they are not sending. I think this should be the second round.
Yes, this is for the second round now.
I know
See, once we start talking of generating, like this generation of this polynomial is still happening in the first round,
Okay.
right?
This first one.
okay.
Like we need to generate this polynomial, this new polynomial, before we can even talk of a new Sumcheck problem. If we don't generate this polynomial, then what Sumcheck problem again are we talking about?
Sorry, so at what point was that round end? Because you, from a particular this thing, you sense the univariate. Like at first, you evaluated speaking A, just putting in B and C. You got the univariate, right? That's what the prover did.
and then he sent that univariate and the sum to the verifier. And the verifier just used the univariates, evaluated as 0 and 1, then check if they're equal. And then when they're equal, and sample a random challenge, and then sent that challenge to the prover. So now, what does the prover do? That, I want to know how that round ends before we now start another round.
The prover needs to generate.
So that random
This-
challenge becomes
The first round, right?
Yeah, the first round.
The first round.
Like still in that first round, after the verifier sent the random challenge, we now need to generate a new polynomial that we are going to use for the next round.
after the verifier sends that random challenge. So the prover uses that random challenge to.
The prover uses the random challenge to generate the new polynomial.
That
So
is
how does it generate the polynomial?
by-
Is it evaluating that random challenge now becomes B abi?
That random challenge becomes A.
A. So it will
Okay, yeah, now evaluate at A, skipping B and C.
Between B and C.
So
Sorry,
so that polynomial will now evaluate that polynomial.
Oh, that will now be the next input for the second round.
Yeah.
Prover sends the polynomial first to me and the sum.
Yes, this polynomial.
Yeah, this
like,
polynomial and the sum.
Basically, this polynomial, the prover and the verifier knows it already, so there's no need for the prover to even send it. So, what the prover sends is this sum and the univariate polynomial, which is this.
Okay, yeah, sorry.
You get? So the prover sends this sum, which is the proof of this sum over the Boolean hypercube, which is this, right?
That's 0 and 1.
Yeah. So the verifier sums, like evaluates as 0 and 1 and checks if it's equal to the sum the prover said. So is it making sense?
Yeah, but from all these things, where does the first round start?
Start.
Yeah.
Start. Please answer.
When the prover sends the lyrics to me and the
And the claim sum.
That's the first round.
Yeah, that's it.
That's where it starts. So the prover is saying that initial polynomial that two of us know, the sum over the Boolean hypercube is 10. Right? And this f of a polynomial is a proof.
So you say both of them know it.
The both of them know.
That's why you call it the public one.
No, that's not even the public one.
Because you said when we did Shamber, you said the transcript is like well converting the public coin.
But the public coin is about the randomness, not about the polynomial. So the public coin is basically that the prover or the verifier will send the random challenge to the prover, and the prover is going to know the random challenge. You can think of it that way. Because the prover will evaluate the initial polynomial at the random challenge. Unless the verifier wants to by himself evaluate that initial polynomial at the random challenge. Maybe he wants to hide the randomness from the prover for one
That'll
reason
make it
or the other.
private.
Yeah, that'll make it a private coin.
I was thinking from it's just the prover that knows
But both of them can know it. The both of them, like people are thinking of this thing like concretely.
Can you bring it down to
No, like I'm saying it's possible that the both of them can know it.
Okay.
It's possible that the verifier knows it and sends it to the prover. The prover needs to know it for the prover to even do any work on it. Right? And it's possible that the prover knows it, but the verifier doesn't know it. The prover always needs to know it. Right? When we talk of like the zero knowledge aspect, the prover is now trying to hide that polynomial from the verifier. That's why we talk of zero knowledge.
Okay.
You get. So it's possible that the verifier, the prover and the verifier knows it. Yeah. It's possible that the verifier knows it and sends it to the prover. You can think of that as computation delegation. The verifier wants to perform a computation, he sends it to the prover. He delegates it to the prover. The prover needs to know it. You get. Then it's possible that the prover knows it, but he don't want the verifier to know it. That's where zero knowledge now comes in. So it's hiding it from the verifier. You get. But that's not just like everything about the zero knowledge aspects. Like there are some mathematics involved in making it actually zero knowledge. Okay. So does it make sense how the prover sends that univariate polynomial and the claimed sum to the verifier? Please, everybody, are we following?
Yes, sir.
Are we sure?
Yes.
Are we sure?
Yes.
Just to get some when we were doing it before, we are doing it now. Why exactly five times like random now?
It's the same thing. You know, before we're using coefficient form, but it's like a lot of people were thinking of like it seems the coefficient form, like we're doing coefficient form example and then implementing in evaluation form. So I think a lot of people were getting it mixed up. Yeah, just evaluation form. It's still the same thing. You can use anyone. Yeah, but this is faster. But you can use anyone. So after the verifier has evaluated at 0 and 1 and checked if it's equal to the claimed sum, the verifier samples a random challenge and sends it to the prover. For the prover to use that random challenge and get a new polynomial in lesser number of variables. Right? So when we now have that new polynomial in lesser number of variables, which is this 10b plus 3bc, we now still need to perform some check over this new polynomial.
That's where the next round starts.
Yeah.
So at the end of the first round, what is the last thing the prover sends?
The prover. This new polynomial.
It's not
Don't you
really
get don't send the claim sum.
No, this is not univariate. But maybe I should just allow you people to implement it. Let me just allow you people to implement it. So you get. Eh? As long as you understand. You get.
Yeah.
Let me just, because maybe I'm trying to make people, some things people are feeling is important. I'm trying to make people see why it's not important, but why the protocol is still secure, even if those things are not really. But then, like, I think you guys should just implement it. So now we have a new polynomial.
And a new claim sum.
Yeah, so that new polynomial now we need to generate a new claim sum for it, right? Because the sum of that new polynomial over the Boolean hypercube can never be equal to the sum of that old one. Yes, because they are different polynomials. Although they are linked together, they are different. So we need to generate the claimed sum for this new polynomial, which is 23. So that is now what we take back.
Start again.
We'll start again. The new claimed sum now will be 23. And this polynomial now, instead of 2ab plus 3bc, it will be 10b plus 3bc. Right? The prover will now generate a new univariate polynomial f of b. Right? Which should be equal to the evaluation at 0 and 1, technically. The verifier now evaluates this new polynomial, right? This new univariate polynomial at 0 and 1 and checks if it's equal to 23.
At the end of the first round, at the end of the first round, that is when we have that 10b plus 3bc generated,
Yes.
which is in evaluation from that 0, 0, 10, 10.
Yes.
So does the prover evaluate the sum?
The sum.
Yeah.
Yes, the prover needs to get the sum because in the new round, the prover is now proving that the sum of this 10b plus 3bc is this new sum.
So this is what the user now, this is what the verifier, sorry, the prover sends to the verifier that now starts the next round. Right?
Yeah, you can think of it that way.
Okay, what actually happens? Like what does the prover actually send? That the
You can-
verifier computes on?
You can think of it that way. You can think of it as like the prover can send this to the verifier. You get? You can think of if that's like
I'm still trying to understand like what ends the round and what starts the next round.
okay. So ending the round is when we've gotten this. Yeah, this new polynomial. So the prover now needs in the next round. The prover now needs to prove the sum of this new polynomial over the Boolean hyperpolary.
So when the round ends by the prover sending this to the verifier doesn't do anything on that polynomial.
No.
So it just samples the random challenge and then continues.
Yeah. So it just samples a random challenge and gives it to the prover.
And that now, because of that random challenge, the prover reduces this to that univariate again.
Yes.
And then gives it to the
And
verifier.
sends that univariate to the verifier. So you can see that like
I'm trying to see the repetition that is happening there.
yeah. So you can see that it's basically that univariate polynomial that the verifier needs.
Yeah.
Not actually this one.
Yeah, because that is easier to
Because that is the one the verifier needs to evaluate as 0 and 1
zero.
and check if it's equal to the claimed sum. But if you want to send this to the verifier, it's design decision. You get no. It seems like when I was trying to like make people understand why there's no need, it seems I was confusing a lot of people. That's what it's looking like. It seems I was confusing a lot of people. But it seems you understand it now, right? So anyhow you want to implement it. It's, does it make sense? Favor. Is it making sense?
I think I get the principle where what we are trying to send to the verifier is just the numeric polynomial and the claim sum. And at every point in time, that's all they ever get. Right? And then they can use that numeric polynomial and claim sum to figure out if the initial polynomial they are actually trying to
Proof.
is valid. But now my question, I don't know if we've gotten that far, my question now will be that in this case where we have 0, 0, 10, we would now have to do another build-up of L. In the build-up of B, rather, reduce this to a univariate polynomial, and that's what we get sent to
To the verifier. That's in the next round
the next
now.
round.
So we'll use this and this as the polynomial and the claimed sum in the new round. Is that making sense? Are we sure? I wanted to talk about like how the verifier can generate this claimed sum by himself without the prover sending it. But I don't know if it's necessary.
Yes.
Huh? Let me allow people to implement. Today is meant to be implementation. This one already. Okay, let's.
So like, if the provider doesn't send things from manual, the car just generates it by itself. That means that it's not really necessary for the verifier to be comparing those intermediate claims from.
No, it's necessary because this is the claimed sum of the new polynomial.
Okay, so if it's not getting it from the provider, so what is it comparing it against?
The verifier will get this claimed sum of the new polynomial,
Okay.
but the prover will now send a univariate polynomial. Like the verifier is getting this claimed sum from f of a. The verifier is using f of a to get the new claimed sum of the new polynomial, but then the prover will send f of b. I hope I did not confuse you.
Yeah, I think when it statements that you said that the verifier will have the claims without the
Prover sending
Prover
it.
Without the prover
I
sending.
think that's the thing.
That's what I
You
was
create polynomial will allow you get take some. You create polynomial you are sending will allow us to take some. If that makes sense.
Okay. Should I explain it?
Yes.
Please, if I'm explaining it anywhere you get lost, drag me back. But before I even start explaining it, I want to be sure that all of us understand this current, like what needs to be done at this current step. Like we understand everything we've done so far.
Yes.
Are we sure? Mitch, do you understand?
This men are looking at you to know that I'm following up.
Eh,
I'm not asking questions. I'm not asking questions.
why are you following?
Yes.
No, that yes, the way you.
I don't want to lie. I don't want to lie, but yes, I'm getting it.
Ekarika, you're just thing with understands this thing.
No, the second guy is doing something else. I'm not this.
Yes.
What are you serious?
He understands this thing. He has finished implementing Sumcheck. Oh.
Sumcheck.
Okay.
This is for Sumcheck now.
Yeah, this
I
one.
am understanding today.
You understand it today. That means you're not understanding it now. You want to understand it
The
today.
information will help me understand it better.
But that we're here so that if you have any question, you ask. It's somehow that's like I keep repeating if you have any question, ask. Maybe like it's possible that some of us may not understand this thing, but we don't even know how to ask a question, right? But I always try to make us understand that even if you don't know how to word the question, just pour out your heart. The way it's in your heart, just pour it out. Anyhow, somebody will understand it and reword the question. You get? So anyhow it's in your heart, like just pour it out. Somebody will understand it and like help us reword the question. Okay? Please. Thank you. Okay, so now let's talk about how the verifier can get the claimed sum of the polynomial for the next round, even without knowing the polynomial. We understand the first round, right? The prover sends a polynomial f of a univariate polynomial f of a, f of a,
Yeah.
f of a, f of a. I know why I'm repeating it. I know why I'm repeating it. The prover sends a univariate polynomial f of a, and the verifier evaluates it at 0 and 1, and sums it and checks if it's equal to the previous or is equal to the claimed sum, right? The verifier then samples a random challenge. At the point of the verifier sampling a random challenge, the verifier can automatically know the claimed sum of the next round. At the point of the verifier sampling the random challenge, the verifier can automatically know the claimed sum of the next round. Does that make sense?
Yes.
The how, forget the how for now, but does what I said make sense?
Yeah.
At the point of the verifier sampling the random challenge, the verifier can automatically know the claimed sum of the next round. Yes. The verifier can automatically know the claimed sum of the next round. You know, when the verifier samples the random challenge, you have not even gotten to the next round. Right?
Yeah.
But then, as at the point of the verifier sampling that random challenge, he can know the claimed sum. He doesn't even know the polynomial.
Yeah.
It's not
From the
predicting.
univariate polynomial that it has before, you just put in the random challenge.
Thank you. You get. So this univariate polynomial f of a, f of a, f of a. So, don't mind me, please. So this univariate polynomial, actually, when the verifier samples the random challenge, the verifier can evaluate f of a at the random challenge to get a point. That point is expected to be the claimed sum of the new polynomial, like in the next round. Does that make sense?
Yeah.
Okay. Let's see something. I've already solved it. I don't know if we're paying attention. But let's go over it again. The verifier samples, like, let me start from here, right? The verifier samples a random challenge. He sends it to the prover. The prover evaluates the polynomial, or partially evaluates the polynomial at the random challenge, right? To get a new polynomial, right? This new polynomial, which is this, right? The prover then needs to evaluate that polynomial over the Boolean hypercube and sum it to get 23, right? This would have been easier to explain if you people understood the graphical representation. But let me now go into the graphical representation so that I don't throw you people away. So, when the prover generates this polynomial, right, and sums it over the Boolean hypercube to get this, the prover then needs to generate a new univariate polynomial. Now I've gone to the next round, right? We're talking about the prover now. Let's wait on the verifier. The prover then needs to generate a new polynomial, a new univariate polynomial, f of b, right? F of b, f of b. Okay, so the prover needs to generate a new univariate polynomial f of b. Calm down. So the prover needs to generate a new polynomial f of b such that a new univariate polynomial such that if the verifier evaluates it, sorry, no, don't worry. check now. Alright. So that f of b, when the verifier evaluates f of b at 0 and 1 and sums it together, the verifier is expected to get this claimed sum, right?
Yes.
Does that make sense?
Yes.
F of b, when the verifier evaluates f of b at 0 and 1, the verifier is expected to now get this claimed sum,
Yes.
which is the sum of this one over the Boolean hypercube. But now we're saying that the verifier already knows this value, right? And that the verifier can know that value by evaluating f of a at the random challenge. Let's see if it works, right? Let's see if it works. So this is f of a, right? 3, 7. Our r is 5. If we evaluate f of, okay, we've seen this one. The claimed sum is 23, right? So let's now evaluate f of a at 5 to see if we get 23. If we evaluate f of a at 5 and get 23, that means it works, right?
Yeah.
We agree. So this is our y0, this is our y1, right? What's our formula?
Y0
y0 plus r y1 minus y0. Our y0 is what?
3.
Sorry, our y1 is what?
13.
Y0 is 3 plus, what is our r? 5, 7 minus 3. So that's 3 plus 5, 7 minus 3 is 4, right? So which is 3 plus 20, which is so do we agree now that as at the time the verifier samples the random challenge, the verifier can know the claimed sum of the next round?
So it doesn't need to receive
Yes,
that.
it doesn't need to receive.
It doesn't need to receive it from the prover, right?
Yes.
But you can as well send it, right?
If you don't, everything is always living, but if you don't perform this back and forth, what's the point of this address? If you have to perform it back and forth,
The essence of ZK, right? Like everything we are doing in ZK is just to prove that polynomials are equal. Like when Wisdom talked about the Strasbourg lemma, right? Two polynomials of degree d can agree on at most how many points? D plus. Is it D plus one? Or we need to verify that. Well, at least okay. So two polynomials of degree d can no, don't worry. So two polynomials of degree d can agree on at most d points. Right? Two polynomials of degree d can agree on at most d points. So those two polynomials, a polynomial. Let me not take us away. Now, I don't want to confuse. It's easy to just jump on another thing, hoping that when we talk about that thing, it will make what we left to talk about it easier to understand. But then that jumping may just throw everybody off, right? But okay, let me just, before I talk about that, let me be sure that we understand this. Do we understand this? And do we understand why the prover doesn't necessarily need to send why the prover only needs to send the first claimed sum to the verifier?
On the verifier can be able to check the claim sum for the next one that the provider is sending back to us.
Yeah, basically the verifier, like that initial claimed sum, that is the claimed sum that is kind of like the most important, right? Because with that one, that is what enables us like start the process. Then after that one, the verifier can generate other claimed sum by
Yeah.
himself.
But isn't that more work for the verifier? Because
More
you could
work
have
for the
just done
verifier.
f of 0, f of 1, and then compare.
But how about if the prover lies?
Well, it would the comparison
When we get to
will
the
not work.
oracle check, the verifier will still catch him sharp. Yeah. So that's kind of like more work for the verifier, right? But it's just the evaluation of, we can't call it work per se, right? Because the major work is the evaluation of that multilinear polynomial. You can think of all those other ones as just checks. Evaluating as 0 and 1, you can think of it as just a check. It's a line, right? It's not much work. Okay, so the whole concept of ZK is just about proving polynomial equality, right? So, and one way we can, two polynomials of degree D, let's say polynomial f of A and f of B, of degree D, let's say D is equal to, what should we use, 10, can agree on at most D points, right? If these two polynomials are the same, they are going to agree at all points, right? If these two polynomials are actually the same polynomial, they are going to agree on all points. It's just like taking the same polynomial and evaluating it at the same point. You're still going to get the same value. But if these two polynomials are not the same, the only, like these two polynomials of degree D, if they are not the same, the only time we are going to evaluate two of them, like the two of them are of degree D, the only time we are going to evaluate the two of them and get the same point is if they overlap, right? And they can only overlap on at most D points. Since they are degree D, they can only overlap on at most, sorry, D plus, yeah, they can only overlap on at most D points, yes. Not D plus 1, not D plus 1. D is the degree. You need D plus 1 points to uniquely define a polynomial. So if they agree on D plus 1 points, then it's the same polynomial. You get? Makes sense. Is it making sense? Is everybody with us? So two.
Sorry, said at D. What happens at D?
So D is the degree of the polynomial, and we need D plus 1 points to represent a polynomial of degree D. So if two polynomials of degree D are equal at D plus 1 points, then it's the same polynomial. It makes sense, right? So two polynomials of degree D can, like two polynomials of degree D that are not the same, can agree on at most D points. Does that make sense? So these two polynomials, a polynomial, you can get a polynomial by multiplying two polynomials, right? You can get a polynomial by adding two polynomials, right? So you can decide to break this guy up, or you can decide to break this guy up into like two factors, right? You can decide to break this guy up into two factors. That is two different polynomials, right? breaking it into two factors does not change the fact that, let's say one of those factors is like f of b and f of c, right? F of a, if f of b and f of c were gotten from f of a, f of a is still equal to f of b times, like, let's use multiplication now, right? F of c. I don't lost you now. Abi? Huh? No, I'm just saying, like, if we actually broke, okay, let's say if we actually used addition to get f of b and f of c, then here will need to be like an addition, right? But what I'm just saying is that, okay, maybe I'm overgeneralizing it. Let's talk of polynomials and their roots, right? Yes, the roots. I'm hoping that I've not thrown in people off somewhere. So I just want to use polynomials and their roots to explain what I'm driving at. So we have a polynomial that has, let's say, 10 roots. 10 is too much, right? Let's say 6. We're not going to solve it out. No, we're not solving it out. We have a polynomial f of a that has 6 roots. So let's say those 6 roots are x minus 1, right? X minus 2.
You mean a minus
Eh?
you mean a minus
Okay, sorry. Thank you. Let's make this x. You get x minus 4, x minus 5, x minus 6. So these are the 6 roots of this polynomial. To get the main polynomial itself, we just need to multiply them, right? And we're going to get this polynomial, f of x. Right? What is the root of a polynomial? The root of a polynomial is all the factors of a polynomial, right? So if we evaluate a polynomial at its roots, we are going to get 0, right? So basically, for x minus 1, for x minus 1, okay. So x minus 1 is a root, right? If we want to get the factor, what are we going to do? Right, equal to 0. So the factor is 1, right? So if we evaluate this polynomial at 1, we are going to get 0. Why? Because that will be 1 minus 1, right? Which will be 0. 0 times all these things is 0. Right? Makes sense? Sure? Sure? I hope. Oh. One is a factor. Sorry, 1 is a root. X minus 1 is a factor. Yes. So 1 is a root of this polynomial. But yes, because if you evaluate that one. So any of these numbers here, like basically this polynomial has 6 roots. So basically 6 factors, right? And if we evaluate this polynomial at any of these points, we are going to get 0. Any of these points in this domain, 1 to 6. If we evaluate this polynomial at any of these points in this domain, 1 to 6, we are going to get 0, because 1 to 6 are factors of this polynomial. Does that make sense? Are we sure that makes sense?
Yes.
That means different values of x are equal to 1y. Since y is 0.
Yeah, they are going to give those different values of x will give us y equal to 0. Yes.
Because they are roots.
Yes. So it's just where it's crossing
Yeah.
the x-axis, right?
Okay, it's one of x at that point.
Yeah. So you can think of the polynomial as like something like this. So all these places it cross the x-axis, y is 0. So those are roots of the polynomial. Is it making sense? Are we sure? Are we sure? Well, we don't come up for some check. Okay, but it's necessary. I'm hoping that, like, with what we've done already, like implementing, we should not be even talking about some check again. Like, you people will be able to implement some check now. With what we've done already, like, so this one is just extra. I'm hoping. But if it's not, please, people should ask questions. Let's address it. Okay, so let me continue what I was driving at. So we all agree that 1 to 6 are factors of this polynomial f of x, right? And we know what a factor is and what a root is, right? If I bring out another polynomial, f of a, okay, say f of x, let's still be f of x, equal to x minus 1, x minus 2, x minus 3, right? And I bring up another polynomial f of x to be equal to x minus 4, x minus 5, x minus 6. Is it true? Is it true that, let's call this 1, let's call this 2, let's call this 3, right? Is it true that f1 of x is equal to f2 of x times f3 of x? Is it true? How is it true? How is it true? We're just multiplying, right? It's true, right? What's going on? So we agree, right? So even if when we expand, is it expand they call it? Expand, right? So even if when we expand this, we're going to get like a different polynomial, right? Of say degree 3, right? And we expand this, we get a different polynomial of degree 3, right? And this one is a different polynomial of degree 6. That doesn't mean that when we multiply there, we're not going to get back this initial polynomial, right? So basically, that is basically just what ZK is about. We have a polynomial, right? And somehow we break it down into smaller polynomials that should still be equal to the original polynomial, right? So if you know those smaller polynomials, then you should know the big polynomial.
So just previous question.
Yeah.
All these protocols now that like real applications of it. I don't know whether the question is making sense. So well, since you are saying there is no small polynomial to get into that one, what power polynomial?
What?
What is the biggest power?
The biggest power?
Yeah, that they work.
Man, those powers are big. That's all I can say. You get for the stack protocol, right, that works over univariate. You know, when you're using multilinear, that kind of like reduces degree of the polynomial vary, kind of like
Multiple
exponential.
variables.
Yeah, but multiple variables. But like those variables will now be like to be linear in those variables, right? But stack protocol that like deals with univariate polynomials can be talking of like degree 2 to the 30,
Dignity.
like 2 to the 30.
To the power 30. Just power 30.
Yeah, actually.
So that's like x raised to power 2 raised to power 30.
Yeah.
No, not x raised to the power 2 to the power 30. Just 2
to
to the. Okay, yes,
Yeah,
yes,
that's
yes.
it now.
Yes.
Hello?
I thought, yeah, so they actually big. They actually big. So tell me you want to be evaluating a polynomial in degree 1 million. How fun is it? Very fun, right? And very sweet. Actually, that's a lot of work, right? That's a lot of work. That's why we kind of like try to look for a way to reduce that to smaller polynomials that the verifier can just work with, but then still be sure that it's still equal to the main original polynomial. Okay, so I hope this helps us understand some things, maybe not everything, but some things. So this was like a side stuff. So let's go back to Sumcheck. Does anybody have any question on Sumcheck? Please one
Yes,
thing.
I continue from where you stopped. That point where you said the prover doesn't need to send that polynomial and the sum, so you can just use like the f of a, evaluate it at the random challenge, and then it gets the sum. So can you continue from that point?
That's at FD.
That is the
That's
verifier.
starting, yes, that point where you want to start the next round, but then the verifier has like completed the claim sum.
Okay. This here, right? Okay. So, are we doing it on the prover side or on the verifier side?
This one now, like the verifier has
Calculated this by evaluating f of
Yes.
a at
So
r,
yes,
right?
yes. So now like the continuation.
Okay. So the continuation is just it's
Next
still
round.
huh?
That's the next round.
Yes, that's the next round you're basically talking about.
Yeah.
Right. Okay, so for the next round, the prover then needs to prove that the sum of this polynomial over the Boolean hypercube is 23. Right. So we go about the Sumcheck protocol again. So this 00, 10, 13. Right. So that's 0, 0, 10, 13, and the sum should be 20, 23. Right? So the prover sends a univariate polynomial. What would that univariate polynomial be? F of b. Right? To be equal to 0. Do we agree?
So evaluating C at 0 and 1.
Yeah. But do we agree?
Yes.
Sure? Okay. So, we've gotten this guy. The verifier is now expected, like the prover sends this guy and the claimed sum. The prover sends this guy and the claimed sum. Verifier is expected to evaluate this as 0 and 1 and check if it's equal to the claimed sum. Right. So the verifier just does, which is 23. Right. verifier samples a random challenge. What should we use?
16.
I used to this much more.
Okay, let's use 60. You see that solve it though. Okay, so the verifier samples are equal to 16, right? So f of b on the verifier side now, let's get the claimed sum for the next round. That will be this y0, this y1, right? So that will be 0 plus 16, 23 minus 0, which is basically like 16 times 23. And what is that? Uh, so, is it 368? Okay. So, next, the prover actually now needs to evaluate this polynomial at r or f of b equal to 16, right? Let's do it in coefficient form so that it's easy for us. That was 10b plus 3bc. So that's 10b, where b is 16, plus 3, 16c. That's 160 plus 48c, right? So this is the univariate, sorry, this is kind of like the last polynomial, right? And the prover, so this is the polynomial we're going to use for the next round, right? So the prover needs to evaluate this polynomial over the Boolean hypercube, which is just 160 plus 48, right? Because the prover needs to get the claimed sum of this new polynomial, right? Are we following? So will be equal to, evaluating it as 0 will be 160. Evaluating it at 1 plus 160 plus 48.
You're evaluating them when you got that R was 16, you substituted it in that polynomial that started the fresh round.
The new round.
Not
Not the initial. Because we have already reduced the Sumcheck problem to a new problem over a new polynomial in lesser number of variables. Makes sense, right? So now we're meant to evaluate this at c equal to 0, c equal to 1, which is 160 plus 48, which is that's 208, right? So this claimed sum will be 208 plus 160, right? Which is 368. But the verifier knew this already, right? So the verifier knew it. The verifier was just waiting for their prover. Okay. So let's just wait a bit for them to bring the light. Okay. So does it make sense up to this point? Are we sure? Sure. Good. So the prover for the new round, right? This is a univariate polynomial. Or this the polynomial that the prover is trying to prove. That is sum over the polynomial per cube is 368. Right? So it's meant to send a univariate polynomial to the verifier. But this in itself is a univariate polynomial. Right? This in itself is a univariate polynomial. So it just so the verifier just works with it. Right? The verifier evaluates this polynomial at 0 and 1. Right? 0 and 1, which is basically what the prover did to get the claim sum. Right? So the verifier does it. Checks if it equals the claimed sum. Yes, which it equals already. Right? And after the verifier does that, the verifier samples a random challenge. Right? So when the verifier, what should we use as a random challenge? 48, okay. Oh.
You know you're making this thing hard.
Let's survive the last one. Let's go ahead and we're going to want to.
Okay, so the verifier samples are equal to 48. But we know that with that, basically, the verifier already can calculate what the claim sum will be. So no need for sending that R to the prover. So the verifier just evaluates 160 48.
I have a question regarding this.
Okay.
So even it's the standard, I know that this works fine, like it's even it is our life, but even if it's the standard that a like the public coin interactive so like you have to return the like random value to the prover. Do you understand? Like I know that you are doing the same like prover now, but it's not that we should return it to the proof.
We should include the claim sum in the proof.
We should from the verifier. I know our transcript is mimicking our verifier. Right?
Yeah.
I know that everything happens in the proof, right? But isn't it right? I mean, the standard that it returns a random, but not to the proof itself, but to like the function.
When the verifier does this, the verifier still adds it to the transcript.
The random number.
Yes.
Okay. Those two works. So I was just wondering. I know it works, but I was just wondering. Is it not the standard? It's not the definition.
Of the protocol, right?
Yes, of Sumcheck, because like that's to get from that. I know it all happens in the proof engine now, but I don't know. Maybe we should just.
Like that's what I said. Like different people are going to have their different implementation. Now we're talking of like the implementation wise, right? Yeah. So, and when you want to apply these things in the real world, maths is easy to. What is? Let me not talk now. Let them not come and rest. But it's easy to solve maths, right? And say this should be equal to this. But when it comes to representing those things in a computer, you need to start thinking about space complexity, you need to start thinking about time complexity, you need to start thinking about like network effects, right? Bandwidth, um, and all these other things. Yeah, all these other constraints. So you want to optimize for those things, right? The goal is to optimize for those things, because if you don't optimize for those things, then you can basically not apply this in a real world setting.
Okay, so
No, ask.
okay.
Yeah.
So this doesn't affect the after schedule. After schedule is still returning the random value,
Yeah.
but before the prover
No. Like the same thing we're sending. The verifier is calculating it by himself, but he's still going to append it to the transcript.
Yeah.
So, in as much as he's appending it to the transcript, they are still going to generate the same randomness. You get.
Yes, I get you.
So, good and fine. The prover was meant to send the claimed sum so that the verifier can check, right, and now append that claimed sum to the transcript. But since the verifier can calculate the claimed sum by himself, he just adds the univariate polynomial to the transcript, calculates the claimed sum, adds it to the transcript, and then samples the random challenge. The both of them are still going to get the same
I agree with you.
random challenge.
That's okay. Thank you.
So, but I get your point. Like textbook definition of the protocol.
Yes.
I get your point. But it's just like based on space complexity now, because the proof will be a whole lot bigger, right?
Yes, exactly. What is like, you know, what is the proof? The proof is the sum and the univariate polynomial. So does it mean that the proof now is only going to be univariate polynomial
And the initial claimed sum.
and the initial claim sum?
And that's the first.
Okay, that's
The
the
first.
proof that.
Well, sorry.
That's the proof that are going to be getting it for every round. Initial claim sum and the univariate polynomial.
Yeah. But like you can have like just one proof where you have the vector of the univariate polynomials and then that initial claimed sum.
Yeah.
You get. So I think I know where you're going, where you have like say a vector of proofs.
Yes, what is the proof?
So in that situation now maybe you're having a vector of proofs, like every round has its proof. Every round has its
Yes.
proof.
It's not like we even need this proof eventually, but it's just like what I was thinking maybe. But I guess this works too.
Yeah, it works. It works.
Sorry.
Even the way you're going about it still works. Too. Everything is just yeah.
Yes, I was asking, since the, what's it called? Since the verifier, right, and the apparently the non-interactive reaction, since they both know like the initial phenomenon, right? Is there any need for your Sumcheck proof to contain the initial claim sum?
No need.
Alright.
For your Sumcheck proof to contain the initial claim sum,
Yeah.
not the initial. There is need for the initial claim sum,
Why is
but there is no need
Because-
for the initial polynomial. The verifier does not want to do that work.
So, the initial claim sum, if the verifier has like the
Initial polynomial.
what's
The verifier, the work is too much for the verifier. I know the verifier can easily sum it over the Boolean hypercube, right? But say that array is actually 2 to the power of 30 elements. Does the verifier want to do that?
But what I'm saying, like, we probably never need that claim sum in terms of like performing the oracle check, right? Your oracle check is basically saying the evaluating the initial polynomial at ABC should be equal to the last univariate
At C.
at C, right? So where are we using that initial check sum basically?
In the
Are
first
they not
round.
different?
In the
But isn't it that initial claim sum, but isn't it in the first round? That first univariate polynomial in A. When the verifier evaluates it at 0 and 1, it should be equal to that initial claim sum.
okay, I see. before going on.
before going on to do.
That's good.
Makes sense, right?
So, but if you don't pass intermediate sums, it means that it's until you get to the end you know that the proof is wrong or something.
But since the verifier can generate those intermediate sum by the verifier self.
Like what I'm saying is, if you don't, the verifier can generate them by himself, but
Yeah.
if the prover does not pass them for the verifier to check his generated sum with the prover's intermediate sums, he won't know that the proof is wrong at a particular point until he gets to the end and does the oracle check.
You know. Because he's still adding it to the transcript, right? Like the verifier, but you understand when we said that the verifier can. You understand when we said that the verifier can get the claimed sum of the next round
Yes.
when his samples are, right? So when he samples that R, and that means he knows it, right? When he adds it to the transcript, if the prover did another thing and add his own another thing to the transcript, they'll sample different challenges,
Can we do example of that?
Those sample different challenges.
different random challenges.
But how does the verifier know that they have sampled a different random challenge?
Maybe when we do it.
At that point.
At that point,
Yes.
when he does that equality check, it will be different.
Which equality check are we talking about?
The f of 0 plus f of 1.
F of 0 plus f of 1 is to give us the claimed sum.
Yes.
But the verifier won't have that intermediate claimed sum that the prover has gotten.
No.
He won't have
No.
it
See,
because we're not passing it.
okay, so like when we get to which point was that? Okay, let's say this point, right? And so this is a point where the prover sends the univariate polynomial to the verifier, right? Okay, so the prover sends the univariate polynomial to the verifier here, right? The verifier evaluates it at 0 and 1, right? And gets the claimed sum
Yeah.
and checks if it's equal to this guy.
Which guy? If it's equals to that sum.
Yes, this claimed
Are we
sum.
talking of interactive? I was talking of non-interactive.
Yeah, even in the non-interactive.
Like
we're
in the
coming.
okay.
Yeah. So after this, before the verifier samples this challenge, right, the verifier needs to send this univariate polynomial and the claimed sum to the transcript. You get to act as randomness to generate this R,
Yes.
right? So on the prover's own end, the prover also, like after he generated this f of b and the claimed sum, he also added it to the transcript.
Yes. Yes. Edit in transcript.
He added it to the transcript, right? So if that claimed sum, if the 12, the same sum that the 2 of them got were different,
Okay.
right? When the prover samples a random challenge again for the next round, they are going to get 2 different R based on the randomness.
They'll sample 2 different challenges.
2 different challenges.
Okay. Now on the verifier side, since he's communicating with the transcript, he has sampled his own challenge at a particular step. Let's say step 2, and the prover sampled a different challenge at step 2. At step 2 too.
Yeah, I said so. Yeah.
So how does the verifier know that the challenge the prover sample is different from his own challenge.
Because
If
it would affect the univariate polynomial that the prover is meant to send.
okay, it will affect the univariate polynomial.
Because you can remember for the prover to generate the polynomial, he needs to evaluate
From the sum
eh?
to generate.
Yeah, for the prover to generate the polynomial that we'll use in the next round,
Yeah.
he needs to evaluate that polynomial that he was proving. Okay. Okay. So basically, like, for the prover to be able to generate that the polynomial we're going to use for the next round,
Yes.
he will be evaluating the polynomial for that round
Yeah.
at the random challenge.
Yes.
So if they sample different random challenges, that means this polynomial is going to be different.
Okay, so he'll be comparing the polynomials. That is the verifier now.
So once it's
Once the polynomial is different, the claimed sum will be different.
So how is it?
The claimed sum will be different.
Yes.
Yes. But okay, no, the reason I'm asking now is okay, the verifier does not want to go to the end and do the oracle check.
No, that oracle check must be done.
Must be
It's
okay.
it's what it's even possible. I don't want to go into that now, right? But it's even possible for the prover to lie, the univariate polynomials that the prover is sending. The prover will probably just be lying about it. You get? And maybe he has a very big computer that can actually generate a false proof, right? But when we get to the end of the protocol, that oracle check would catch him.
Catch him.
Yes.
Okay. So with the way we're saying the proof now, which is just the initial sum and what was the other one?
And the univariate
Yeah,
polynomial.
the univariate polynomials. That means that the verifier can't stop halfway. If he can't do
And
any check
just
halfway,
agree.
and just he can't do any check halfway to say okay, at this point I already know that the proof is wrong, and so I don't have to go to the oracle check.
No, he can't.
He can't.
Because if the univariate if this polynomial is different, then the univariate polynomial will automatically be different.
Yeah. So okay, what would
And-
make him stop halfway? What would make him? What check will he do?
This
Say, okay, I've checked and I can stop now.
this check,
What will he do?
that is the polynomial.
That gives the claimed sum.
Yes, this will give the claim.
So he will check this claimed sum against what?
This is a univariate polynomial.
Yes.
This claimed sum is a concrete value.
Yes.
You get.
Uh-huh.
So if this univariate polynomial is wrong, when we evaluate it as 0 and 1, we are not going to get this
Yeah,
claimed
that's the check.
sum.
That's the check I'm asking.
Yeah.
Yeah, that's the check I'm asking. Thank you.
But does it make sense?
Yeah, it makes sense.
It makes sense, right? So this, based on the randomness, this thing is basically forced. The claimed sum is forced. So we're not telling the prover, based on this claimed sum, give us the right univariate polynomial.
Okay.
You get?
Yeah.
But if the prover had lied by maybe picking another R that is not the right R, then the univariate polynomial that the prover is going to get will be different. When we check it, it's not going to equal, yes, at 0 and 1, it's not going to equal to that claimed sum. Does that make sense? Are we sure?
Yes.
I have a question. So, Sumcheck, how many, when we start each round, we get 2 polynomials. You want to put the sum, then the new one.
Yeah, the new one that we'll use for the next
Is
one.
it books that were appending to our transcript or just
No, just the proof, like
So that
the
new
univariate, just the univariate.
So that new one, not
So no need to append it. Because you sending it is basically like, what does the verifier want to use it for?
all those artists who are not storing them.
No, we're not storing them. We're just sending them to the transcript. The transcript is generating a randomness for us.
So that means if we decide not, if the provider decides not to add the claim sum as part of the code, right? I am by the user. But if the provider decides not to send the claim sum with the variable now as part of the Sumcheck proofs, so basically the verifier just gets the claim sum from the univariate at that point.
On the univariate,
Right.
yes.
Then that's what it just passes to the transcript alongside that.
Yes, exactly.
That makes sense.
Exactly. Are we together? Huh? Are we sure? Yes.
When we are talking about this non-desired I think the protocol introduces a lot of I'm not saying a lot of
Forthcoming. Alright. I don't know if I'm going to look into that, but even like over the weekend, like I said, there was a paper that came out. I've not read the paper yet though. But it actually, especially, it's important. It's important to append that initial univariate polynomial to the transcript. That initial univariate polynomial.
The transcript.
Yes. If you don't append it to the transcript, that can be like, so that is kind of like one of the major
So
sources
the
of
initial,
bug. That initial polynomial that the prover wants to sum over the Boolean hypercube, that the one you're starting with to prove. Yeah? Sorry, multilinear. Sorry.
It has to be part of the transcript.
You need to add it to
So
the
all the
transcript.
polynomials are going to be in the transcript, right?
Or which of the polynomial?
For the multilinear, the other multilinear, then each univariate
Then each univariate.
must be in
You
What
need
about
to
the
append it to the transcript
not
with the
like
sums.
With the sums too.
So are you trying to tell me that like basically the starting value of that transcript state should be the initial polynomial?
The randomness, right? What you're using for that initial randomness.
This is confusing now. Okay, wait.
what?
You know, like the transcript needs to absorb something.
Yes. Is the initial polynomial the first
That
thing
should be the
absorbed?
first thing it absorbs.
Like the first multilinear polynomial.
Yeah, that initial multilinear
So that means to
polynomial.
get A now, it's absorbing the initial polynomial,
Yes.
the first claim sum, and the first
And the
univariate.
first univariate.
Okay. Yeah, like
that initial polynomial, the one that the prover wants to, I'm coming. The one that the prover and the verifier wants to engage.
The claim.
Huh?
The claim in code.
Yeah, like you can call it the computation per se. Yeah. So that initial polynomial, you need to append it to the transcript.
the first univariate.
You're also going to append that first univariate at the first claim sum. And then for the other round, you're just appending the univariate at the claim sum. Because I think they found a bug in Grot 16. I think Donado Cash uses Grot 16, right? And they found a bug similar to that. You get
So they were not adding that.
like that initial one. So it's basically like you're trying to prove something, but you're not making the person like commit to that thing. So the person can come later and say it was not what I committed. It was not what that's not the polynomial I gave you the answer to.
Oh.
You get. So he actually needs to commit to it.
Are we adding the what's it called? The initial claim sum.
Yes, the initial claim sum, we're adding it.
So that means it's 4 now to get A.
Yeah. To get A is 3 now. the initial polynomial,
Mm-hmm.
the initial claimed sum, and the first univariate.
Then for
Okay, yeah. That means the claim sum of the first univariate is basically the initial
Is the
claim
initial
sum as
claim,
well.
exactly.
Oh, that makes sense.
The first one, the first univariate or the first multivariate.
First univariate.
The first
Yes,
multivariate.
the claim sum of the first multilinear, that is that
Yes,
initial,
polynomial.
and the claimed sum of the
univariate.
first univariate are the same
Same.
thing.
But what you're not
At that point, it's very validated.
the first thing you just what you do normally is commit the multilinear, commit the claim sum of that multilinear and the univariate.
Yeah,
Yeah.
that's basically what I'm saying. But
Yeah.
I was thinking like they were not the same initially, so that's what I was
They are the same. Because that's basically just f of let's say f of x equal to f of 0 plus f of 1. That's just basically what it is. But don't mind what I wrote so that I don't.
Please,
But this is
I
basically
want
what
to
it is.
ask.
So,
because I was thinking of for the first random that we use 3 values. At the first multilinear, the first invariant, and the
claim sum.
then for the
Other
first
ones.
we just took the sum of and the invariant.
So, hope everything makes.
I think
Okay.
I'll just ask my question.
Yes, please.
At what point do we start looking at it? Is it, do we commit
At what point do we start looking? That's
do we
like.
commit multilinear, commit first claim sum, first univariate before we start looking?
Depends. You can
Now this is like going into like implementation details. Anyhow you want to do it.
You can.
You get.
What is that thing you said? There's something you said that makes this whole stuff vulnerable, the way you set it up. So how do you set it up that it becomes vulnerable so that we can avoid setting it up that way?
Yeah, so that is what I said, like that initial multilinear needs to be appended to the transcript. Yeah, actually done, but is it making sense?
Yes.
So, am I expecting everybody's Sumcheck implementation by tomorrow's class?
By the grace of God.
And Fiat Chimera. Everybody should have done Fiat Chimera by now. No?
You can do all this.
Right? The Fiat Chimera.
That fetch Shemira, there's like normal fetch Shemira.
Do you
There's
still
some
get
check
problem
for
for
fetch
that?
Shemira.
Which one are you talking
Shey na you say mo do
The
hard
Fiat
one,
Chimera,
right?
like, it's implement it as a library. So you're just instantiating a transcript and you're interacting with the transcript.
What we did yesterday.
What we did yesterday was the transcript. We just coded the transcript.
And then
So you need to now import that transcript into your prover and your verifier and interact with it.
The transcript is fetch.
Yes, the Fiat Chimera transcript.
that interacting with it as
In the Sumcheck protocol. So you're not implementing the transcript inside Sumcheck. You get? You're not implementing the transcript inside Sumcheck. You're just calling the transcript that you've implemented already, and then you interact with the transcript. Does that make sense? Okay, so so by tomorrow, we're actually meant to do. We've been postponing it, so we're meant to do like a review, everybody's implementation. So if your implementation is not up to date,
Sorry.
please.
Professor. Sorry, you said you asked us to add the initial prediction.
You are taking us
Wait.
back.
We don't.
I thought
Did you say anything like that?
Yes.
That we should add the initial polynomial.
yes,
To
to
the
the
transcript.
To the
transcript.
commit.
But before you said it was not necessary to do that.
Now we have seen the
Now
problem.
don't change.
We have seen the letter.
Wait, when did I say that?
Like you said, two of them have that initial polynomial.
I said don't add. No, it's not necessary to add it to the proof. The proof and the transcript are two different things. Don't confuse
You
them.
want, you want the line on top meant.
Okay, like do we add it to that to the Asha, to the
Yes,
what the Asha
Yes,
is
that's
already-
what I'm saying.
That is
Yes. But you don't need to add it to the proof. The proof structure. The proof structure. Does it make sense?
It's like the game.
So please can you give us like an
No, again,
I'm not giving any interface
Like,
No, it's just
Which other interface? Guy?
which kind of like,
No, but what interface do you need again?
We have a verifier, the reason why I'm doing that is that the prover can come and entry and say,
Yeah, those are three entities. You have a verifier, a prover, and you have a proof. The prover proves and generates a proof. The verifier takes the proof. The verifier also takes the initial polynomial because he knows it. The verifier also takes, okay, the claim sum is in the proof, right? So the verifier takes the proof and the initial polynomial and either accepts or rejects. This is sounding like magic.
no, I'm thinking of the code. I understand what you said, but I'm thinking of the implementation.
Okay, let me give, maybe I bring the light. Let me just write out like an interface, right? We have the proof. That's why I'll write it out that when they bring the light. But okay. What's going on with the light? Let them not burn.
This light is
Yeah. Okay. So by tomorrow, I'm expecting everybody's Sumcheck implementation by tomorrow. Eh? We understand the protocol, right? Is there anybody that does not understand the protocol?
so the interactive is not called Shamia. What is it called?
It's still Sumcheck. The both of them are still Sumcheck.
No, like it's not called Shamia. Like what is it called? The non-interactive is Shamia.
The non-interactive is still Sumcheck protocol.
Yeah. Like that name, Fiat Shamia.
Fair Shamia is just the process of making the interactive non-interactive.
I was looking for naming convention.
But does everything make sense? Okay, so the proof will have the claim sum and the univariate police.
That's a vector.
Yeah, a vector. Right?
Only those two.
Yeah.
Okay.
The prover should be able to call, you may want to be able to instantiate a new prover, right? So maybe prover new, anyhow you want to do it. It's your own design
Pattern.
decision. So after instantiating, the prover shall have prover proof. Prover proof should take an initial polynomial and return a proof.
You take an initial polynomial.
That is the initial polynomial it wants to work with. So you can instantiate it. You can as well, maybe when you're creating your prover, you just put the initial polynomial and then in the prover.
Okay, that's
You get.
that's the struct.
Yeah. So anyhow you want to define your prover struct, right? So the prover shall have a proof that takes an initial polynomial, if you had already defined the initial polynomial in the prover structure,
Take self.
yeah, you can now take self. You get. So you take the initial polynomial and it returns a proof, right?
Yeah.
The verifier,
So the proof only has two methods, two functions, new and proof.
So that means all that interaction with the transcript and everything is happening inside this proof.
it's happening inside the proof.
Yeah.
I think this already like
Makes it clear, right?
makes a lot of sense.
Yeah. So the verifier has the verifier verify, right? Verifier can as well have new, right?
Yeah.
So it can create a new verifier with a polynomial. Yeah, you can as well implement it. Okay, let's put it. Verifier new, right? In new, if you want to put your polynomial here, that one is your own design decision.
But then
Also-
that proofer that is having the new there, that's the
You can as well put your poly here.
but
So-
inside that proofer now, is that where we're going to instantiate the transcript?
Yes, that's where you're going to instantiate the transcript. Anywhere you want to, if you want to instantiate it in the new, okay. If you want to instantiate it in proof, okay. I bet instantiate transcript is just to call transcript new,
Yeah.
right? Right?
Yeah.
Okay. So, this expo I'm giving you people. If people don't implement it before tomorrow, we'll fight. Eh? Verify, exactly.
The referral also needs to instantiate its own transcript, right?
Yeah, you can instantiate it in the new, or you can instantiate it in the verify. Yeah, the verify also needs to instantiate its own transcript that is going to interact with. Okay, so verifier verify is going to take proof and it's going to take initial. Oh. Okay, so verifier verify is going to take the proof and the initial polynomial. It's not necessary to take the initial polynomial if you instantiated it already when you were instantiating the verifier, right? But all those ones is implementation. Yes. So
But then that means if you put it in the new, that means if you want to reuse the verifier, you have to like reinstantiate, right?
if you want to reuse the
Yeah, verifier like for a new computation, you have to reinstantiate.
instantiate, exactly. Yes. Yes. Also, there was something about. Okay, but does this? Okay, sorry, let it come on. It's 217. Okay, but does this make sense?
Yep.
Does this make sense?
Yeah.
Makes sense, right? But if it doesn't, ask questions. Ask questions. Ask questions. So there was something with yesterday's generate random challenge. That yesterday when we generate the random challenge, right? If we want to generate another random challenge, we'll need to like absorb back that random challenge, right? But you can just like do it internally in that function. That this thing you're hashing, that output you're getting out, you can absorb it again. Yes. Yes, instead of now in your protocol having to go to put it back to absorb. Right. So that anytime you sample a random challenge, you mutate states.
Okay, like you're saying that anytime you sample a random challenge, like absorb that
Yeah,
challenge.
absorb that challenge internally in the function. So that you know that when you're coming again to call, you're getting a different an updated challenge.
So that other steps will build on the previous one.
Yes. Because if you don't do it like that, then you now need to absorb, like in your code now, you'll be absorbing the univariate polynomial, the claimed sum, and the challenge again. You get? I've lost you guys. Really, is that look on your faces?
Okay, okay, I get.
So just internally, just update it. So I think with that,
So
like,
for this year, you're right. The approval always needs to send the claim sum for each step because the claim sum, because you vary its polynomial, needs to be absorbed to form the
to get the new challenge, yes.
But in the normal sum check, it doesn't always need to send the claim sum because the verifier can always get information.
In the non-interactive,
Yes, in non-interactive.
yes. Okay, so I think with that we've come to the end of today's class. Implementation by tomorrow. Like when? No, tomorrow. Next tomorrow we are going into. Next tomorrow is Friday, so we are going to like do a review.
We're going to go.
Next tomorrow, like
Some
GKR.
next week now.
And introduction to GKR. Like, actually, but like tomorrow will be like implementation, right? Today was meant to be implementation, but like I hope what we covered today will help make the implementation easier, right? So
Are you checking like how efficient is your addition implementation?
no, it doesn't need to be efficient for now. Yes, just let the protocol work and let it be correct for optimization with time personally. So for now, just get the crude implementation working. Hope that's okay. Okay, so I think we've come to the end of today's class.